In this section, we'll discuss the Ethereum blockchain. We'll dive into how it works and how it can change the current economic ecosystem. The Ethereum blockchain could be the foundation for our digital future. It's open to everyone, no matter your location, background, religion, skin color, age, or education, and all you need is a digital wallet to take part. Ethereum builds on Bitcoin's innovation, along with some big improvements. So Ethereum allows you to send value using its native cryptocurrency called Ether, which is equivalent to Bitcoin, and to run smart contracts that are decentralized applications or dApps. There are dApps for finance, real estate, social media, gaming, and many more. Note that the name of the blockchain is Ethereum and the name of the cryptocurrency is Ether or ETH. Any value like money, ownership rights, real estate ownership, shares, registries of debts or promises that can be stored in a centralized ledger can also be stored in a decentralized manner on the Ethereum blockchain. So, in a nutshell, Ethereum is used to send value or digital money called ETH or to run decentralized applications called smart contracts. Smart contracts will govern the economy of the future. The Ethereum blockchain is an immutable public database that stores records of all the transactions that have ever taken place. A transaction is used to transfer digital money or to run smart contracts. Then you should know that Ethereum is a Turing-complete blockchain. It means that we can put it into code and solve any computational problem, no matter how complex that is. Ethereum is also a disruptive technology because it's decentralized, more private than the normal internet, and censorship resistant. Let's dive deeper into this and explain what it means. Decentralized means that there's no central person, company, or entity that could in a centralized manner control or shut down the applications. Ethereum runs unstoppable applications. Once a smart contract, which is in fact an agreement translated into code, is deployed on the Ethereum blockchain, it runs forever and cannot be stopped. If we take a classical web application, let's say Twitter, there's a central company that controls everything. They could simply shut down the servers and everything is gone. Or they can ban or censor you with or without a warning or reason. Ethereum is a censorship-free technology because there's no third party that can interfere with it. Censorship is not possible on Ethereum. Nobody is able to stop Ethereum or a dApp that runs on it because it runs on thousands of independent nodes or clients. It's a peer-to-peer network and it allows you to move money or make agreements directly with the other party. You don't need to go through intermediary companies. Then, smart contracts are immutable and run forever. There's no downtime on Ethereum. Once a transaction is saved into the blockchain, it cannot be altered. In the case of a classical application where data is stored in an SQL database, anybody that has rights can run SQL statements such as update or delete and modify or remove the data. On Ethereum, anyone can send transactions to the blockchain, and once confirmed, those transactions cannot be reverted. A classical financial company such as MasterCard or Visa or your bank can stop transactions, revert them, or even freeze your account if they wish. And finally, remember that Ethereum is more private than the normal internet because you don't need to provide your identity to have a wallet and transfer value or run smart contracts. Okay, we went through the main characteristics of Ethereum, which are common to many other blockchain technologies. We'll take a short break, and in the next lecture, we'll discuss Ethereum nodes. In the last lecture, we've seen what is the Ethereum blockchain and what makes it such a disruptive technology. Now, we'll take a look at its components. Ethereum is a peer-to-peer network of computers named Ethereum nodes or clients. each of which runs a compatible client software. Anyone can run an Ethereum node, and there are no special prerequisites or requirements. At the moment, there are thousands of Ethereum nodes that communicate with each other. Take a look at ethernodes.org, where you can see statistics about the Ethereum mainnet. Most of the clients run Geth on Linux and are from the US, Germany, and China. Geth, short from Go Ethereum, was programmed in Go programming language and is one of the original implementation of the Ethereum protocol. There are more ways for a user or application to communicate with the Ethereum network. Web3.js is a collection of libraries that allows web applications to interact with an Ethereum node using HTTP, IPC, or WebSocket. It's the official JavaScript API developed by the core Ethereum team. A normal website cannot communicate with the Ethereum blockchain, so you'll need Web3.js. Another way is to use a wallet. A wallet is a piece of software that has access to the private key, controls the Ethereum account, and can interact with Ethereum dApps. MetaMask is a well-known crypto wallet and gateway to Ethereum dApps. There are also a bunch of other Ethereum wallets that can be used to interact with different applications running on the blockchain. Take a look at this page on ethereum.org, where you can choose a wallet based on your preferred features. Let's go back to Ethereum nodes. An Ethereum node runs a virtual machine called EVM, which is short for Ethereum Virtual Machine, which in turn runs applications, or EVM bytecode. The applications it runs are based on a global consensus mechanism. This EVM has its own microkernel, stack, memory, and storage. You should know there are three different types of node. Full node, which stores locally a copy of the entire blockchain, participates in the block validation and verifies all blocks and stakes. Light node, which stores only the header chain and requests everything else, and can verify the validity of the data against the stakes in the block headers. The light node clients are useful for low-capacity devices which cannot afford to store gigabytes of blockchain data. And the archive node, which stores everything kept in the full node and builds an archive of historical stakes. It requires terabytes of disk space, which makes archive nodes less attractive for the average users. You can run your own node, but before installing any client, please make sure that your computer has enough resources to run it. Depending on which software and sync mode you are going to use, you'll need an SSD drive and hundreds of gigabytes of disk space. Also note that there are new clients for Ethereum 2.0 that run the beacon and shard chains and support the new proof-of-stake consensus mechanism. Okay, that's all about Ethereum nodes. In the next lecture, we discuss Ethereum accounts and addresses. We'll start talking about Ethereum accounts. There are two account types in Ethereum: externally owned account, EOA, and contract account, or CA. Both account types have the ability to receive, hold, and send Ether and other tokens, and to deploy and interact with already deployed smart contracts. An externally owned account or user account is controlled by a private key identified by a unique address and has no associated code. This type of account is managed by a human, not by a contract. If you want to hold, send, and receive ETH, all you need is an EOA. You can create such an account for free using one of many wallets available. If you are a beginner and want to create a new account, I'd recommend you to use MetaMask, which is a browser plugin, or MyEther Wallet, which is a web service and the client-side interface that interacts with the Ethereum blockchain. We'll create an Ethereum externally owned account in both MetaMask and MyEtherWallet shortly after we discuss contract accounts. A contract account can be created by an externally owned account or by another contract account. It has a unique address, same as the externally owned one, but no private key that controls it. It's controlled by the contract code only. Note that because it uses the network storage, creating a contract account costs gas, so in fact money. A contract account can only generate a new transaction in response to receiving a transaction from an externally owned account or from another contract account. The triggered transaction means code that gets executed by the EVM on the Ethereum blockchain, and this can be anything from transferring tokens, calling a specific function, creating another contract, and so on. Let's take a look at the components of an Ethereum account. The nonce is a counter that indicates the number of transactions sent from the account. This is a mechanism used to ensure that the same transaction isn't submitted twice. For a contract account, this number represents the number of contracts created by that account. The account balance in Wei, where Wei is a denomination of ETH, and there are 10 to the power of 18 Wei in an Ether. Another component is the account address. Both the externally owned and contract accounts have an address. We'll see shortly how the address for each type of account is determined. And the account private and public key only for the externally owned account. So the EOA is made of a cryptographic pair of keys, public and private ones. The private key is randomly generated by the wallet libraries and is used to sign transactions. So the private key grants custody over the funds associated with the account. Note that in fact, you never really hold cryptocurrency, you hold the private key that can unlock the funds that are always on the Ethereum blockchain. And at point number 5, we have the code. Only a contract account has code. This is the immutable EVM bytecode. And the storage only for the contract account, which is empty by default. Let's take a look at this diagram from Ethereum EVM illustrated. You can also think of an account as a mapping between the address and the account state. The account state contains the nonce, the balance in Wei, the storage root hash, and the EVM code hash. At the end, I want to explain how the key pair and the address of the account are generated. When you create a new account using a wallet, a random private key is generated. It has a length of 256 bits and is represented as 64 hex characters. The private key can be encrypted with a passphrase, and it's vital to keep it secure. Then, from the private key, using ECDSA, which is short for Elliptic Curve Digital Signature Algorithm, the public key is generated. The address of an externally owned account is derived from the last 160 bits or 20 bytes of the public key that are hashed using the Keccak 256 algorithm. It's represented in hexadecimal format, which is often indicated explicitly by adding 0x at the beginning. The address for an Ethereum contract is deterministically compound from the address of its creator, the sender, and how many transactions the creator has sent. So the nonce. There's a lowercase address version and the partial uppercase version that also contains a checksum. Okay, we are taking a short break, and in the next lecture, we'll create external owned accounts using both MetaMask and MyEtherWallet. Let's talk about gas, which is essential for the Ethereum network. The platform needs gas to run in the same way as a car needs gasoline to function. What is gas? Gas is the unit that measures the amount of computational effort required to execute specific operations on the Ethereum network. Any operation is part of a transaction that requires computations resources to execute on the blockchain, and the user that runs the transaction must pay a fee that is proportional to the resource it consumes. Gas refers to the fee required to successfully execute a transaction on the Ethereum network and is paid in ETH. Gas was introduced to make a practical distinction between the actual market valuation of the ETH cryptocurrency and the computational costs of using Ethereum's virtual machine. Gas fees also keep the Ethereum network secure because it prevents a hacker from attacking the network with a denial of service attack because he has to pay money for each basic operation. The gas price is the amount of whey the sender of the transaction wants to pay for the unit of gas for the transaction to be mined or processed. The gas price is given in gigawhey or billions of whey, which is the smallest denomination of ETH. The miner node will include the transaction in a new block, takes all the gas, so the fees of all the transactions in the current block, and then all the other nodes of the Ethereum network will run the transaction. So only the miner takes both the block reward and the fees, and all the other nodes just execute the transaction. The Ethereum protocol defines how many gas units each basic operation consumes. Let's take a look at this web page where you can see the EVM operational codes known as opcodes. The additional operation costs 3 gas units, the multiplication operation costs 5, or the modulo addition operation 8 gas. To make it crystal clear, I've made this spreadsheet for you where you can see the most common operations on the Ethereum blockchain together with their costs in both ETH and US dollars. The spreadsheet is attached to this lecture. I've considered the standard gas price as being 90 gigawhey per unit of gas, and the ETH price as being $2,000. So, the operation to create a new smart contract costs 32,000 gas, and that means 5.76 US dollars. To send a new transaction costs 21,000 gas units plus the gas for all the operations in the transaction. So a standard ETH transfer requires a gas limit of 21,000. And that translates to 3.78 US dollars. To save 256 BICs on the blockchain storage costs 20,000 units of gas, and to store 1 megabyte to the storage costs this incredible huge amount of gas, which translates to 100,000 US dollars. I know you are thinking that at this price the blockchain is unusable. But you should know that you don't usually save bulk data on the blockchain. You can use other decentralized off-chain solutions such as IFS or interplanetary file system. Another remark is that I've considered the standard gas price as being 90 gigawhey per unit of gas. Can you pay less than that? Can you say, I want to pay only 10 gigawhey per unit of gas? And the answer is yes, you can, but it won't work. The new transaction will not be mined or included in a new block. That's because the miners will sort and then select the transactions that are waiting to be mined by their gas price. And if you say, I pay only 10 gigawhey and another user pays 90 gigawhey, his transaction will be mined and yours won't. There's a limit to the number of transactions that can be included in a new block, and that limit is based on the gas price, which is dynamically set by the network. Take a look at ethgasstation.info. At the moment, the standard gas price is 80 gigaway, and the transaction will be mined in less than 5 minutes. If you pay 90 gigaway, the transaction will be mined in less than 2 minutes. And if you are a trader and want the transaction to be included in a new block as soon as possible, then you should pay 97 gigaway per unit of gas. So faster operations will likely charge higher fees. If you refresh this page at a later time, you'll see here other values. Also note that most of the wallets automatically set the gas price for you to a recommended value that you can adjust if you want. Let's see another example. Let's suppose that a transaction has 3 operations. A multiplication that costs 5 gas according to the protocol standard, an addition that costs 3 gas, and an equality comparison that costs 3. So the total amount of gas the transaction needs is 11. Now if the gas price is 50 gigaway or 50 billion way, then the transaction fee will be 50 gigaway multiplied by 11 equals 55 gigaway. And if you want to see the fee in ETH, you can go to ethconverter.com and see that 55 gigaway is this amount of Ether. Now that you've understood what the gas and the gas price are, let's talk about gas limit. Each transaction sets a limit called gas limit to the maximum number of computation steps of code execution can use. Let's go deeper into it. For each transaction, there are 2 variables, the gas price, and we've just talked about, and the gas limit. This is the maximum units of gas a user wants to pay for a transaction. This is required because it's very hard to estimate in advance how much gas a transaction would require. Think of the gas limit as a security mechanism that prevents high fees from being incorrectly charged due to a bug or an error in a smart contract. Let's return to this slide. So, besides the gas price I want to pay, I also have to set the gas limit. So, let's say gas limit equals 10. For our simple example, if I say the gas limit is 10, then the transaction will fail because it required 11 units of gas. This is, for example, a real transaction that ran out of gas and failed. The gas limit, so the maximum amount of gas provided for the transaction, was 96,629, but it required more. Let's return to the slide. If I say gas limit equals 21,000, like this, which is the standard for a regular ETH transaction, then my transaction will succeed. That doesn't mean that it will consume 21,000 gas. It will consume only 11. Any gas not used in a transaction will be returned to the user. So you can see that what really defines the value paid for transaction fees is the gas price, not the gas limit. Note that Ethereum has a block gas limit rather than a block size like Bitcoin. To develop dApps or smart contracts for the Ethereum blockchain, we need an integrated development environment or IDE. We'll start talking about Remix, an open source IDE that allows developing, deploying, and administering smart contracts for the Ethereum blockchain. It supports both Solidity and Viper, the two programming languages used to develop smart contracts. Remix has its own compiler and JavaScript virtual machine and can be used as an online IDE, or you can install it locally on Windows, Linux, or Mac. So there are two versions available, an online IDE and a desktop app. Through this course, we'll use the online version because we can start right away and develop smart contracts straight from the browser. If you wish, you can install it locally by clicking on Get Our Desktop App and then download and install the latest release from GitHub. Note that Remix is written in JavaScript and has modules for testing, debugging, and deploying smart contracts. It can be used for the entire journey of smart contracts development, as well as Playground for learning Ethereum and Solidity programming. Let's access the online version at remix.ethereum.org and create our first smart contract. You can access the File Explorer section by clicking this icon. By default, Remix IDE only stores files in your browser's local storage, but it's possible to go beyond this default behavior. Pay attention that clearing the browser storage will permanently delete all the Solidity files stored there. This is an inherent limitation of a browser-based IDE. The File Explorer's browser folder has a sample project on it. There are a few samples of Solidity smart contracts and JS files. To create a new file, select the folder, click on the new file icon, type a name, like say my contract, that's all, and press enter. And the file has been created in the selected folder, in this case the contracts folder. You can also create folders to organize the files of your project in a specific way. Click on this icon to create a new folder. The next icon will publish all files from the browser folder to a gist, which is a repository that can be forked or cloned. And to upload a file from your computer's file system to your browser's local storage, click the last icon, this one. And if you right-click on a folder or a file, you'll get a context menu to rename or delete the file or folder. Okay, I think that's enough because it's intuitive, so let's get to coding and create our first smart contract in Solidity. For the moment, don't focus on Solidity syntax because we'll have lots of sections where we'll dive really deep into it. Just focus on how to use Remix to create and deploy smart contracts. So, I'm opening the file called mycontract.sol I've just created. Every source file should start with a comment indicating its license. And I have pasted the comment from the clipboard. By the way, you can increase or decrease the font size by clicking these small icons. Then, the pragma keyword is used to enable certain compiler features or checks. So I'm writing pragma solidity 0.8.0 and a semicolon. We'll talk more about pragma later in this section. And the name of the contract will be property. So contract, this is a keyword, property, and a pair of curly braces. And I'll define a state variable that will be saved in the contract storage on the blockchain. So int public value. The name of the variable is value. It's a public one of type int. Don't focus on these details too much. We'll have a lot of time. And I'm creating a setter function that will be called when wanting to change the value of the variable. So function, this is a keyword, xName, let's say set value, the function's parameter, let's say int underline value, and the keyword public, and a pair of curly braces to start the function's body. And in the function, I'm writing value equals underline value. This will set the value variable to the underline value parameter. And that's all. This is a very simple smart contract. To deploy the contract, we have to compile it, meaning we have to transform the source code into bytecode and deploy the bytecode. To access the Solidity compiler, click the Solidity icon in the icon panel. This is the Solidity compiler panel. I'm selecting the compiler version, which should be 0.8, because this is what the pragma directive says. And I'm clicking Compile my contract. It's compiling it. Great. If there are any errors in the source code, the line with the error will be highlighted in red. I'm making on purpose an error by removing the int keyword, which specifies the variable type and is mandatory. And I'm compiling the contract again. The contract was not compiled and it's indicating there's an error on line 8. You can see more details about the error on the left side below the contract section or in a pop-up window if you mouse over the line. And it says identifier not found or not unique. I'm making it right again. If there are any warnings, they are displayed below the contract section as well. To trigger a warning, I'm removing the first line, which is the comment that indicates the type of the license. And I'm compiling the contract again. There's no error, but there's a warning. It says SPDX license identifier not provided in source file. I'm putting the line back. Now there's no warning. If you want the file to be compiled each time the file is modified, check the auto-compile checkbox. Now it is being compiled as I type. And there's an error. I have removed the semicolon, which is mandatory. The contract was compiled without pressing the compile button, and I have a warning. There's an unused local variable. Okay, we are taking a short break, and in the next sections, we'll talk about compilation in depth, abstract binary interface, bytecode, and deploying the contract. Welcome back. Let's dive deeper into Ethereum smart contracts and see how to deploy on the Ring-B testnet using Remix and MetaMask. This is a more real-life approach because the testnet is like the mainnet, just that we don't pay for gas. So we need the MetaMask plugin with an Ethereum account that has a balance of ETH. In the last section, I've shown you how to install MetaMask and how to fund an account using the Ring-B authenticated faucet. Take a look there if you feel the need. We'll deploy the first contract, so let's get started. In the MetaMask window, select the Ring-B testnet. Then, go to Remix and click on Deploy and Run Transactions. And then choose Injected Web3 Environment. It will automatically use MetaMask, so a new window pops up and you are prompted for the wallet password. I'm entering the wallet password. And I'm unlocking the wallet. And it was unlocked. If it's asking to connect to Remix, confirm it. If I open the MetaMask window, I see that MetaMask and Remix are connected. In the left upper corner of MetaMask, it says Connected. Also check that the account has a positive value of ETH to pay for the gas. The next step is to deploy the contract. I'm clicking Deploy and a new MetaMask window is popping up. In this window, I'll set up the gas I want to pay for the transaction. This is given in gigawei per unit of gas. The larger the value, the faster the transaction will be mined. If you deploy it on the main Ethereum network, you'll follow the same steps, just that you'll pay real money for the transaction. MetaMask will update the gas price dynamically according to the current network status. You can see the recommended value for the gas price on ethgasstation.info. I'm deploying on the testnet, so the gas price is not so important. I'll increase the value anyway. You don't change the recommended gas price in most of the cases, except the case when you want the transaction to be mined faster. And I'm clicking Confirm. The transaction has been broadcasted, it's pending, and I'm waiting for it to be confirmed. In a few seconds, a new window will pop up that says that the transaction has one confirmation. In the Remix console window, I see a link to the Ring-B Block Explorer, and I can click on it to track the transaction and get more info about it. This is the transaction on Etherscan, and there are already 2 block confirmations. Now the contract state is live and anyone can interact with it. Let's interact with the contract. Back to Remix, I'm creating and sending a new transaction to change the value of the state variable called value. So, in the Deployed Contracts section, in the Property window, I'm entering a value and clicking the Set Value button to call the function. Let's say 55. The function will change the blockchain state, and that means that it has to be mined, which is not free. The MetaMask window is popping up again. I'm checking that it's on the Ring-B testnet, and I'm entering a value for the gas and clicking Confirm. Mining the transaction takes some time, so at the moment, the value on the blockchain is still 0, not 55. After a few seconds, it's confirmed, and I'm clicking value again. And the new value of the variable was fetched from the blockchain, and it's now 55. That's all. This is how you send a transaction that deploys a contract or interacts with an already deployed contract using Remix and MetaMask on the main or test Ethereum network. You've already seen a very basic smart contract, and you now know how to deploy it on the Ethereum blockchain. Let's talk about the layout of any smart contract that is programmed in Solidity. A smart contract is an agreement translated into code between two or more parties, and the trust will be better established if the contract source code is available. If you make the source code available, you'll touch on legal problems with regards to copyright, so the Solidity compiler encourages the use of machine-readable SPDX license identifiers. SPDX, the short for Software Package Data Exchange, is an open standard used to document information on the software licenses under which a given piece of computer software is distributed. So every Solidity source file should start with a comment indicating its license. The Solidity compiler doesn't validate the license, but it will include the supplied string in the bytecode metadata. If you don't supply the SPDX license, a compilation warning will be triggered. Next comes the pragma keyword, which is used to enable certain compiler features or checks. Pragma indicates the version of the Solidity compiler that should be used to compile the current file. This way, an incompatible change introduced by a future compiler version will be rejected. Pay attention that new versions of Solidity are frequently released, and some of them introduce incompatible changes. If a compilation fails, I'd advise you to check the compiler version you are using and also read the breaking changes introduced by each Solidity version on docs.soliditylang.org. For example, these are the breaking changes introduced by version 0.8. The version pragma is used as follows: pragma solidity caret 0.8.2. A source file with this line does not compile with a compiler earlier than version 0.8.2, and it also does not work on a compiler starting from version 0.9.0. The second condition is added by using the caret symbol, this one. Let's test it. I'm selecting compiler version 0.7.6 and click compile. And we see we've got an error. Source file requires different compiler version. You can also allow compiler versions between two specific values. For example, pragma solidity greater than or equal to 0.5.0 and less than 0.9.0 will allow the source code to be compiled by compiler versions that are greater than or equal to 0.5 and less than 0.9. So this pragma line is valid. Note that a pragma directive is always local to a source file. So if you import other files in the current one, you'll have to add the pragma to all your files to enable it in your whole project. And when deploying contracts, you should use the latest released version of Solidity because breaking changes as well as new features and bug fixes are introduced regularly. Next, we are seeing the contract keyword and the name of the contract. The contract source code is placed between a pair of curly braces. This is the contract source code. The name of the contract will not be saved on the blockchain. At deployment, each contract receives a unique address that will uniquely identify the contract. Contracts in Solidity are similar to classes in object-oriented languages, so each contract can contain declarations of state variables that will be saved on the blockchain, functions, function modifiers, events, structs, and enum types. There are also special kinds of contracts called libraries and interfaces. Take a look at this contract. There are two state variables declared: price and owner. Price is of type uint or unsigned integer and is private, and owner is of type address and is public. Their values are permanently stored in contract storage. Then we see some functions defined. The first function is a special one called constructor that is used to initialize the state variables of the contract. It's declared with the constructor keyword, and when a contract is created, its constructor is executed once. Change owner and set price are called setter functions because they change the value of state variables, and getPrice is a getter function because it creates a call that returns the value of the state variable. There's also a function modifier called onlyOwner that changes the behavior of the function to which it is applied. In this case, it's applied to changeOwner, the one that changes the value of the owner state variable. And at the end of the contract, we see an event. Events are features that enable logging functionality. This is the general structure of an Ethereum smart contract developed in Solidity. We are taking a short break, and in the next section, we'll dive deep into Solidity syntax and concepts. Even though Solidity isn't more difficult than other programming languages, I wouldn't recommend starting with it as your first programming language. Some basic knowledge of programming in any other language will help you a lot when learning Solidity. As smart contract code is executed on the EVM, it means that eventually this code is executed on all nodes around the network, so on both mining and non-mining nodes. That is why Solidity is a more low-level language than commonly used JavaScript or C++. Let's talk about the basic syntax rules of Solidity. Solidity is a high-level, statically typed programming language for implementing smart contracts. It is influenced by C++ and JavaScript and is designed for the Ethereum virtual machine. However, it was stripped down as it doesn't include any unnecessary features. Let's see the most important rules of the language. Solidity is case-sensitive like any other programming language. Every statement must end with a semicolon, just as in JavaScript or C++. In this example, if I remove a semicolon, a compilation error will be triggered. Expected semicolon. It uses curly braces to delimit blocks of code. This is, for example, the function body that's being enclosed between a pair of curly braces. This is another characteristic inherited from C++ and JavaScript. Solidity uses C++ and JavaScript syntax for writing comments. Writing comments in any programming language is a way of explaining what the program actually does. You can write single-line comments using double forward slashes and multi-line comments enclosing the commented code between /* and */. I'm adding a comment, so I'm starting the line with double forward slashes and then writing some text. For example, this is the constructor. And to add a multi-line comment, I'm writing /* and on the next lines, the comment. And I'm closing it with */. For example, declaring functions, which are the contract interface. This is a multi-line comment. There's a third type of comment in Solidity called netspec that is developed and promoted by Ethereum itself. This is a special form of comments in Solidity contracts used by developers when documenting contracts, functions, libraries, return values, and more. You may use triple forward slashes for a single line netspec or / double stars ending with star and / for a multi-line netspec comment. I'm adding a single line netspec comment. So, triple forward slashes, at notice returns the price of the property. At notice is a predefined netspec tag that explains to the user what this tag does. There are more such tags defined. Most of the classical control structures and loops are available in Solidity too. However, pay special attention to loops. Loops do not have a fixed number of iterations, and for example, loops that depend on storage values have to be used carefully. They could hit the gas limit, causing the transaction to fail. For this reason, while and do-while loops are rarely used. At the end of this lecture, I want to tell you that new versions of Solidity are frequently released, and some of them introduce incompatible changes with previous versions. If you try an example from this or any other course and it fails, I'd advise you to check the compiler version you are using and also read the breaking changes introduced by each Solidity version on docs.soliditylang.org. Welcome back! We'll start diving into Solidity and talk about variables. Solidity is a statically typed language like C++, Golang, or Java, which means that the type of each variable needs to be specified when declaring the variable. So, starting from this empty contract, I'm declaring a new variable of type int called price. Int public price. In Solidity, a variable has also a visibility that can be adjusted, and in this case, it's public. We'll talk more about visibility specifiers later in this section. In Solidity, there are two types of variables, state and local. State variables are declared at the contract level after the name of the contract and are stored on the contract storage, so on the blockchain. Saving state variables on the blockchain is not free and you have to pay gas. According to the Ethereum protocol, saving 256 bits costs 20,000 units of gas. For example, price is a state variable. To declare a constant, so a special variable whose value cannot be changed, use the constant keyword. I'm declaring another state variable called location of type string that is constant. We suppose that the location of the property cannot change. So string, constant, public, location equals, and between double quotes, London. It's mandatory to specify the value of the constant when declaring it. If you omit the value, you'll get a compile error. This is an error, an initialized constant variable. In Solidity, the concept of undefined or null values does not exist. When you declare new variables, they always have a default value depending on their type. For example, the default value of an int variable is 0. So even though I didn't explicitly initialize the price variable, x value was set to 0. Let's see that. I'm deploying the contract on the JavaScript virtual machine and then getting the values of the state variables. Location, London, and price equals 0. We notice that the default value of the price variable is 0. If you try to change the value of a variable after you declare it, you'll get an error. For example, writing price equals 100, it's not permitted in Solidity. There's a compilation error. I'm commenting out this line, and I'm writing this is not permitted in Solidity. To change the default value of a state variable, there are three possibilities. Using the contracts constructor which is a special kind of function that gets automatically executed when deploying the contract, using a setter function, or initializing the variable at declaration. So, at declaration, I'm setting the price to 100. I'm deploying the contract again to have the new updated instance and getting the value of the variable. Now price is 100. Also, be aware that storage is not dynamically allocated. What I mean here is that the number of the state variables is fixed at compile time. This instance of the contract cannot have other state variables besides those already declared. So if I'd say I want to have another variable called owner in this instance, that won't be possible. I have to change the contract by declaring that new variable and then deploy a new instance. All variables must be declared before deploying the contract. Let's move on to local variables. These are variables that are declared and used inside functions and are kept on the stack, not on storage, so they don't save their values between different function calls. They don't cost gas, they are free. Let's declare a dummy function with a local variable. So function f1 public pure returns int between parentheses and the function's body. Int x equals 5, x equals x star 2, and return x. This is the function. I have declared the function pure because it doesn't touch the blockchain. It neither modifies the blockchain nor it rigs from the blockchain. X is a local variable that is free and is saved on the stack. Note that there are some types that reference the storage by default even if they are declared inside the function. They are strings, arrays, structs, and mappings. So, if you want to create a local variable of type string, you have to use the memory keyword to limit its lifetime to the function call and not be saved in the storage. Writing string s1 equals abc results in an error because string is a special type that by default is saved in storage. This is an error. I'm adding the memory keyword to save it in memory, and now everything is fine. Okay, just ignore the warning that says unused local variable. I've declared the variable but never used it. So, there are three zones where data can be stored: storage, stack, and memory. Let's come to a conclusion. State variables are saved in the contract's storage, so on the Ethereum blockchain, and they cost gas. For example, saving 1 byte costs 5 units of gas. Functions' local variables are saved on the stack if they are not reference types and don't cost gas. Functions' arguments and variables declared inside functions that are reference types but are declared using the memory keyword are saved in the memory and don't cost gas. Reference types are type string, array, struct, and mapping. In this lecture, we'll be talking about Solidity functions, one of the core concepts of Solidity programming language. A function is an executable unit of code within a contract. Functions create the contract's interface. Take a look at the functions defined in this contract. There's a function called setPrice, which is a setter function because it sets or changes the value of a state variable, and a function called getPrice named getter because it gets or returns the value of a state variable. Let's talk about the syntax. To create a function, use the keyword function followed by the function name, and a pair of parentheses. If the function has any parameters, write them between parentheses, separated by a comma. By the way, the name of the parameter is underline price to differentiate it from the state variable. So price is the state variable stored in the storage, and underline price is the function's parameter stored in memory. Each function must have a visibility specifier that is given after the parameter list. In this example, both functions are public, which means they are part of the contract interface and can be called internally from the same contract or externally from other contracts or applications. Other visibility specifiers are private, internal, and external. We'll have a dedicated lecture on visibility specifiers later in this section. If the function is a read-only one that doesn't alter the storage in any way, it should be declared view or pure. Note that calling a setter function creates a transaction that needs to be mined and costs gas because it changes the blockchain, and calling a getter function creates a call that happens instantly and doesn't cost gas because it doesn't alter the blockchain state. And if the function returns a value, that should be indicated using the returns keyword and the types of the returns values between parentheses with a comma between them. In this example, getPrice will return a single value of type int. There are no compilation errors, so I'm deploying the contract. I've used the JavaScript virtual machine environment. In the deployed contract section, if we open up the contract, we'll see a button for each function. The buttons were created by the Remix environment. Getter functions are in blue and setter functions in orange. If I click a button, it will call the corresponding function. So I'm clicking Get Price, a call was created, and the default value for the price, which is 0, was returned. Now I'm changing the price value. So I'm typing 100 and clicking Set Price. A transaction was created and sent, and the value of the state variable was changed. Now the price is 100. In fact, it wasn't really necessary to declare the getPrice function because the price state variable is public. When you declare a public variable, a getter function is automatically created. This is the getter function, price. It returns the value of the state variable. Let's change the visibility of the variable location to public. By the way, the default visibility for a variable is private. I'm erasing this instance and deploying the new contract. Now we see a new button called location that is in fact the getter function that was automatically created for the public state variable. Let's create a setter function for location as well. So function set location string memory underline location. This is a local variable, and the function is public. And the function body location, the state variable equals underline location, the function's parameter. The memory keyword is required because explicit data allocation for all variables of type array, string, struct, or mapping is now mandatory. It indicates that the variable will be saved in memory and not in storage. Now I'm deploying the contract. This is the new instance, and we see 4 buttons in the contract section. 2 are getters and the other two are setters. Okay, in fact there are 5 because there's also a getter that was automatically created for price, this one. Now we can change the value of both state variables and get their values as well. I have changed the value of the location variable and I'm getting the new value. Now let's talk about the constructor. The constructor is a special function that is executed only once when the contract is created. The function is created with the constructor keyword, there's only one, and is optional. You can see that the contract we've developed has no constructor. The constructor is used to initialize state variables when the contract is deployed by an externally owned account or by another contract. Let's create the constructor of the contract to initialize its state variables. So, constructor, this is a keyword, and the parameters. Int for the first state variable, underline price, string memory, underline location, to initialize the second state variable. And in the constructor's body, I'm writing price equals underline price and location equals underline location. And that's all. The state variable price will be initialized with the value of the underline price parameter of the function. And the same for location. It's not mandatory for the constructor to have arguments, but it's logical to initialize the state variables so it has 2 arguments. And the visibility of the constructor, which is normally public, should be ignored starting with Solidity 0.7. When I deploy the contract, I'll specify 2 values for the constructor's arguments, price and location. Let's deploy it. So, the price will be 100 and the location Paris. This is the transaction that has created the contract, and this is the contract's interface. The constructor has initialized the state variables with the supplied values, so if I click price and location, I'll get those values, Paris and 100. It's common for a constructor to register the address of the account that creates the contract in a state variable. This is the admin of the contract or the owner, and in most cases, he has full access over the contract. So, I'm declaring a new state variable at the contract level called owner of type address, which is a data type in Solidity and holds an account address. So, address public owner. And in the constructor, I'm adding owner equals msg.sender. Let's look for a second at this line, owner equals msg.sender. What does it do? It initializes the owner to the value of msg.sender, where msg.sender is a global built-in variable. This variable always stores the address of the account that creates and sends the transaction. In this case, it's the address of the account that deploys the contract because that's the only time when the constructor is called. Note that I don't have to declare the variable msg.sender because it's built in and always exists. I'm deploying the contract again, choosing another account, for example, the second one. The address of the account will be stored in msg.sender and it becomes the owner of the contract. I'm deploying it. This is the new instance. And if I click the owner button, I'll get the address of that account. It was saved on the blockchain and I can further implement administrative functions of the contract, like selling the property, functions that will be initialized only from the owner account. This address is the address of the second account. Note that the constructor cannot change the owner to a new address because the constructor is called only once when the contract is deployed. If you want to change the owner, you need another function that changes the state variable called owner, and probably that function can be called only by the current owner. Note that almost any contract, like for example ERC20 token contracts or contracts for decentralized finance, use this approach to register the owner that has special privileges. At the end, let's talk about initializing constant or immutable state variables. State variables can be declared as constant or immutable, and in both cases, the variables cannot be modified after the contract has been deployed. For constant variables, the value has to be fixed at compile time, so we need to set their values at declaration time, while for immutable, it can still be assigned at construction time. So, if I declare a constant state variable, I also have to initialize it with a value. For example, int constant area equals 100. If I don't initialize the constant with a value, I'll get an error. This is an error. Uninitialized constant variable. If I declare the variable as being immutable using the immutable keyword, the variable can be initialized the same as a constant at declaration or in the constructor, but not after the contract was created. So I'm changing constant to immutable. There's no error. Another example would be if I wish no one to be able to change the owner. I can declare the variable immutable and initialize it in the constructor. So the owner is immutable and it's initialized in the constructor. After the contract's deployment, no one will be able to change the variable, so the owner. Compared to regular state variables, the gas costs of constant and immutable variables are much lower, so this allows for local optimization. Solidity is a statically typed programming language like C, C++, Java, or Go, meaning that the programmer must specify the variable type at declaration. We'll start a series of lectures on Solidity data types. We'll dive deeper into booleans and integers, and then we'll move on to arrays, mappings, structs, and enums. Note that floating point numbers, such as float and double in other languages, are not yet supported in Solidity. If you want to perform calculations for a currency like Ether and want to use floating point numbers, then you should use a smaller denomination of ETH that will be represented as an integer. Integers and booleans are also called value types because variables of these types will always be passed to functions by value. This means that they are always copied when they are used as function arguments. Starting from this empty contract, I'll define a variable of type bool. Bool, public, sold. The possible values for a bool variable are constants true and false. I'm not initializing the variable to true or false because I want to see its default value. So even though the contract has only one line of code that declares a variable, I'm deploying it. Being a public variable, a getter function was automatically created. So if I click sold, the getter function is called and the default value, which is false, is displayed. Let's go ahead and talk about integers. There are signed and unsigned integers of various sizes. To declare an unsigned integer that has only positive values, use keywords uint8 to uint256 in steps of 8. The number after uint indicates the bit length of the value that can be stored. So uint8 means an unsigned integer of 8 bits, and the maximum value that can be represented on 8 bits is 2 to the power of 8 minus 1 and is equal to 255. And to declare a signed integer, use keywords int8 to int256 in steps of 8. Note that uint is an alias to uint256 and int is an alias to int256. Let's see some examples. uint8 public x equals 255. This is the maximum value that can be stored in a uint8 variable. And int8 public y equals minus 10. Now, I'm trying an overflow which happens when the value of a number is bigger than the maximum possible value offered by the type. I'm setting x to a value greater than the maximum one that can be represented on 8 bits, which is 255. So I'm setting x to 256. This is an overflow. And the overflow was detected at compile time, and I'm getting a compilation error. We'll take a short break and we'll continue with overflows and underflows, which are of great risk, especially in financial applications. Ethereum is used in many financial applications, and an overflow or an underflow would have disastrous results. In April 2018, two types of vulnerabilities called batch overflow and proxy overflow were discovered in some ERC20 tokens that were built on Ethereum. The result was that tokens valued at billions of US dollars were created from thin air. These are the details of such a transaction. Just take a look at the number of tokens that were transferred. In a response to that attack, many crypto exchanges suspended trading on all ERC20 tokens, causing a great deal of fear, uncertainty, and doubt in the crypto community. Let's take a closer look at how an overflow or underflow vulnerability works. So, I have declared a state variable called x of type uint8, and I've initialized it with the maximum possible value for that type, 255. And I'm creating a new function, function f1, public, and I'm incrementing x, which is already at the maximum value for its type. So x plus equals 1. I'm changing the Pragma compiler version to an older one, let's say 0.5.0. Pragma Solidity 0.5.0. And I'm selecting that version of the compiler, and I'm compiling the contract. Great, there's no error. The contract was compiled successfully, and I'm deploying it. If I click X, I'll get X value, which of course is 255. Now, I'm calling F1 that will increment X. The transaction was executed successfully. Transaction mined and execution succeed. Now, if I click X, I'll get 0, which of course is not correct. So what happens when you have a limit of 255 and you try to do 255 plus 1. The number rolls over, and so 255 plus 1 equals 0. We call this an integer overflow. Just imagine this behavior in a financial application. You have 255 US dollars on your account, someone sends you $1, and then you'll have 0. For those who want to dive deeper into this, I'll attach to this lecture a full technical breakdown of the batch overflow exploit. Let's go ahead and see how we can protect against such events. In Solidity, the standard practice to avoid overflows was to use a library known as SafeMath. SafeMath wraps each calculation in a series of checks to make sure that, for example, when A plus B equals C, C is greater than A and B. This was best practice for every smart contract that was coded professionally. For example, this is the source code of BNB token from Binance exchange used on their platform. This is the source code. See how they use the SafeMath library for math operations with safety checks. Maybe you've noticed that I've used past tense when referring to overflows and use of the SafeMath library. Starting with Solidity 0.8, the compiler includes checked arithmetic operations by default, and this makes unnecessary the use of SafeMath or similar libraries. Starting with Solidity 0.8, arithmetic operations revert on underflow and overflow. Let's compile the same contract with a compiler version newer than 0.8. So I'm changing the pragma to caret 0.8.0. And of course, I'm selecting the corresponding compiler. The contract was compiled successfully, and I'm deploying it. This is the new instance. I'm clicking X to get X value, which is 255, and then I'm clicking F1 to increment X. And instead of creating a successful transaction that causes an overflow, the transaction has been reverted to the initial state. Look at this error. The transaction has been reverted to the initial state. So it didn't alter the variable, which is still 255. This is a big improvement. So now, by default, arithmetic operations are always checked. You can switch to unchecked mode using the unchecked keyword to obtain the previous behavior. And you probably want to do that for old code and backward compatibility. Like this. Unchecked, and the code between curly braces. This code will have the same behavior as in the previous compiler versions. Let's start talking about another data type called array. In programming, an array is a data type that stores an ordered sequence of elements. In Solidity, there are two types of arrays: fixed size and dynamically sized arrays. A fixed size array has a fixed number of elements that are specified at declaration, and this type of array cannot grow or shrink. On the other hand, a dynamically sized array does not have a fixed number of elements, and it can shrink or grow dynamically at runtime. Let's get started with fixed size arrays. Array elements can be of any type, including int, address, mapping, or struct. The only restriction is that all elements of an array must be the same type. Let's declare an array that stores int values and has a size of 3. So uint, a pair of square brackets, 3, the number of elements in the array, public, and the name of the array, numbers. The array is public, so a getter function was automatically created. I'm deploying the contract to see the default value of the array elements. An array is an ordered sequence of elements, so each element is at a position or index in the array. Like in any other programming language, in Solidity, arrays indexing starts from 0 as well. So, the first element of the array is at index 0. This is the first element of the array, and its default value is 0. This is the second element of the array at index 1, and the last element of the array at index 2. If you try to access an element of an array at an index that is negative, greater than or equal to the length of the array, you'll get an out-of-bounds error. For example, give me the element at index 5, and I've got an error. To initialize an array with some specific values, you can specify the values at declaration or create a setter function that changes the elements of the array. So to initialize the array at declaration, write the name of the array equals and the elements between square brackets with a comma between them. For example, 2, 3, 4. By the way, this is an array literal. I'm deploying the new contract and I'm checking the values of the array. The element at index 0, the second element at index 1 is 3, and the last element at index 2 is, of course, 4. Now, I'll create a setter function to change the elements of the array. So function setElement. The function takes two parameters, the index and the value, and is a public one. And the function will change the element at the index with the value. So numbers of index equals value. Okay. Before deploying and testing the new function, let's talk about length as well. An array has also a member called length that stores the number of elements in the array. So I'm creating a new function that will return the length of the array. Function getLength. The function is public. It doesn't modify the blockchain, so view, and returns the length of the array, so a uint. And in the function's body, I'm writing return numbers, the name of the array, dot length, the member. Okay, of course, here is returns, not return. I'm deploying the new contract. This is the instance, and I want to see the number of elements in the array, so the length. And the length is 3. Now, I'm changing the element at index 0. So index 0 and the element will be 100. I'm setting the element, and now I'm getting the element at index 0, and it has returned 100. Great. As I said earlier, the elements of an array can be of any type, not just int. Let's see a special type of array that holds a sequence of bytes from 1 to up to 32. So, bytes 1, public, B1. Bytes 2, public, B2. And bytes 3, public, B3. And we have up to bytes 32. bytes1, bytes2, bytes3, and so on are Solidity data types. Let's deploy the contract and see what are the default values of the arrays of type bytes. I'm deploying it and I'm opening up the last contracts instance. This is B1, B2, and B3. We see that the default value is 0, but it is shown in hexadecimal as the 0x prefix indicates. A byte consists of 8 bits and a hex digit occupies 4 bits. So a byte can be represented with 2 hexadecimal characters, 2 bytes with 4 hexadecimal, and so on. Now I'll create a new function that will change the elements of the array of type bytes. So function set bytes array. And public. And inside the function I say b1 equals a, b2 equals ab, and b3 equals abc. Great. I'm deploying the contract to test the new function. The contract was deployed successfully, and I'm opening up the last instance. So, I'm calling the setBytesArray function. The transaction was successfully mined, and I want to see the values of B1, B2, and B3. So B1 is 0x61, B2 is 0x6162, and B3 is 0x61, 62, and 63. The characters were encoded in UTF-8, which is a superset of ASCII, and are shown as hexadecimal values. Let's search for an ASCII table on Google and check it. Take a look here. The hex ASCII codes for A, B, and C are 61, 62, and 63, like it's shown when calling the function in Remix. We see here the ASCII codes of A, B, and C. Now, if an array is initialized with a value that does not occupy the entire space, padding is added by default to the end. So I'm changing B3 equals Z. By the way, the ASCII code for Z is 7A in hexadecimal. Keep in mind, 7A. And I'm deploying the new contract. I'm clicking Set Bytes Array to change the values, and now I want to see the value of B3. And we see 0x, 7A, the ASCII code for Z, and then lots of zeros. This is the padding. Also note that using indexing you cannot modify single bytes in fixed bytes arrays. So B3 of 0, this is the first byte or the byte at index 0, cannot be modified. This is a compilation error. This is not permitted in Solidity. Single bytes in fixed bytes arrays cannot be modified. If you see some older code, you should be aware that prior to version 0.8.0, byte used to be an alias for bytes1. So byte is an alias for bytes1 in older code. Welcome back. In this lecture, we'll discuss dynamically sized arrays. Dynamic arrays refer to arrays that do not have a predetermined size at the time of declaration. Their size is determined at runtime. Let's create a dynamic array that holds elements of type uint. Note that the dynamic array can hold elements of any type. So the type, uint, a pair of square brackets, the visibility specifier, and the name of the array, numbers. A dynamic array has three members, length, push, and pop. Let's take them one by one. Length contains the number of elements in the array. Let's create a function that returns the number of elements in the array. So, function getLength, public view returns uint. And the function's body is return numbers the array dot length x member. Another member function of a dynamic array is push, and it appends an element to the end of the array. I'm creating such a function. Function add element. uint item. This is the element that will be appended. And public. And numbers dot push the member of item. It's pushing the item to the end of the numbers array. The contract was compiled successfully, and I'm deploying it. If a variable is public, like our dynamic array, a getter function is automatically created. So, let's see the length of the array. And there are no elements in the array, so its length is 0. Now, I'm adding a few elements. 10, the second element 20, and the third element 30. Let's see its length. And its length is 3. Now, let's fetch the elements of the array. The element at index 0, the element at index 1, and the element at index 2. Great! If a variable is public, like our dynamic array, a getter function was automatically created. I've already used that getter when I've fetched the elements of the array. But we could optimize it by adding some tasks. For example, at the moment, if I access an element using an index greater than or equal to the length of the array, I'll get an out-of-bounds error. For example, I say give me the element at index 10, and I've got an error. The call failed. So I'm creating a new function, an optimized one, called getElement. Function getElement. The parameter of the function is the index, uint I, so it will return the element at index I. Public view returns uint. It returns an element of type uint. And inside the function, I'm writing if I less than numbers dot length. So if there's a valid index or the index is less than the array's length, then I'll return the element. Return numbers of I. So the element at index I. There's an warning because I have to add an explicit return for all branches or for all code paths. So here, if I is equal to or greater than numbers.length, I'll return 0. I have to return something. Let's test the new function. I'm deploying the new contract. I'm adding 2 elements, and I'm trying to fetch an element from an unexisting index or from an index greater than the array's size. So I'm saying give me the element at index 10. And there's no error. It returned 0. Another member of a dynamic array, except strings, which are a special type of dynamic array, is pop. Pop is a function that removes an element from the end of the array. I'm creating such a function. So function pop element public. And inside the function numbers.pop. I'm deploying the contract and testing the new function. This is the last instance. I'm adding a few elements, 3, 4, 5, 6, and 7. There are 5 elements in the array. And I want to pop or to remove the last element. The transaction was executed successfully, and now there are 4 elements in the array. The last element, 7, was removed. So the last element at index 3 is 6. Note that increasing the length of a storage array by calling push has constant gas costs because storage is 0 initialized, while decreasing the length by calling pop has a cost that depends on the size of the element being removed. Note that since Solidity 0.6, it's not possible to resize storage arrays and array.length is read-only. The reason behind this is to prevent storage collisions of very large storage arrays. Besides the storage arrays we've just seen, there's another kind of array called memory arrays. The keyword new creates a dynamic memory array. Let's create a function that uses a memory array. So function f public. And I'm declaring a memory array. uint, a pair of square brackets, memory, let's say y, the name of the array, new, uint, a pair of square brackets of 3. By the way, I can set the function mutability to pure because it doesn't use the blockchain. As opposed to storage arrays, it is not possible to resize memory arrays, so the push and pop member functions are not available. You either have to calculate the required size in advance or create a new memory array and copy every element. So I'm initializing the 3 elements of the array with some random values. So y of 0 equals 10, y of 1 equals 20, and y of 2 equals 30. And I'm assigning the memory array to the storage array. So numbers equals y. Of course, if I do that, I have to remove the pure keyword because the function modifies the blockchain, modifies the state variable. So I'm removing it. We are taking a short break, and in the next lecture, we'll discuss bytes and strings, which are special dynamic arrays. Hi guys, and welcome back. We'll go ahead with dynamic arrays and talk about bytes and string arrays. Variables of type bytes and string are special dynamic arrays. String is equal to bytes, but does not allow length or index access. A string is UTF-8 encoded in Solidity. I'm starting from this empty contract, and I'm defining 2 dynamic arrays, one of type bytes and the other of type string. So bytes public b1 equals abc. And the array of type string, string public s1 equals abc. As a rule of thumb, use bytes for arbitrary length raw byte data and string for arbitrary length string UTF-8 encoded data. I'm deploying the contract and checking the values of the arrays. This is B1 and this is S1. And we notice that the values of the bytes array are displayed in hexadecimal, 61, 62, and 63, being the hex ASCII codes for A, B, and C. And the string is displayed normally as a UTF-8 encoded string. One difference between bytes and string is that we cannot add elements to a string variable as we can to a variable of type bytes. So I'm creating a function called addElement. Function addElement public. And I'm writing b1.push, let's say x. I've added an element to the end of the bytes array. But if I try to do the same for the string array, I'll get an error. So s1.push of x is an error. Member push not found or not visible after argument dependent lookup in string storage. Let's test it. I'm deploying the contract and checking the B1 array. It was initialized with A, B, and C in hexadecimal, and I'm adding an element, the element x. Now the value of x, which is 78 in hexadecimal, was added. Another particularity of bytes arrays is that it's possible to access the elements of the array using indexing. So function getElement uint I. Public view returns bytes1. So the function will return an element of the array, which is a byte. So return b1 of I. But if I try return s1 of I, I'll get an error. Index access for string is not possible. And finally, we can get the length of a bytes array using the length member, but we cannot get the length of a string. Function getLength public view returns uint and return b1.length. This is possible, but I cannot return the length of a string. So return s1.length will trigger an error. Member length not found or not visible for strings. Note that bytes and strings are reference types, not value types. And also pay attention that fixed size arrays use less guess than dynamic arrays. So they are better for the situations when the length of the array is known in advance. In the following lectures, we'll talk about structs, mappings, and enums. Structs provide a way to define new data types. It introduces a new complex data type that is composed of other elementary data types. Structs are used to represent a singular thing that has properties such as a car, a person, a request, an auction, or a campaign. A struct can be declared outside or inside of a contract. Declaring a struct outside of a contract allows it to be shared by multiple contracts. Let's declare such a struct. Struct, the name of the type, let's say instructor, a pair of curly braces, and the elements of the struct. uint age, so an instructor has an age, string name, he has a name, and an address, of course, an Ethereum address. ADDR. This is the new type. And I'm creating two contracts in the same Solidity file, Academy and School. So contract Academy, the first contract, and the second one, School. Being declared outside of the contract, I can declare a variable of type instructor, my newly created type, in each contract. So instructor, the type, public, and the name of the variable, Academy Instructor. And the same for the school contract. So instructor, public, school instructor. Now I'm initializing the struct variable using the constructor. So constructor and the following parameters: uint underline age, string memory name, and that's all. Academy instructor, so the struct variable dot age equals underline age, the function's parameter. Academy instructor dot name equals underline name. And academy instructor dot address, dot addr, this is the name of the member, equals msg dot sender. So the address that deploys the contract. Before testing the contract, I'll declare a new function called changeInstructor to show you how to modify a struct variable. So function changeInstructor. And the parameters are uint underline age, string memory underline name, and address underline a double dr. And the function is public. By default, struct references storage. I'm creating a new temporary memory struct, initializing it with the given values, and copying it to the storage struct, the state variable of the contract. So I'm declaring a new memory variable of type struct. Instructor, memory, let's say my instructor, the name of the variable, equals, and this is how you initialize a struct variable. So the name of the struct, instructor, a pair of parentheses, a semicolon, and inside the parentheses, a pair of curly braces, like this. And then age, colon, underline age, comma, name, colon, underline name, comma, and addr, colon, underline addr. And the comma is not required after the last member initialization. And I'm copying the memory struct variable to the storage one. So academy instructor, the storage variable, equals my instructor. Now I'm testing it. I'm deploying the contract. I'm giving 2 arguments to the constructor. So age 30 and the name, let's say Dan. And I'm deploying it. Okay, it was deployed. And I can click Academy Instructor to see the struct. And this is the struct. Age equals 30, name equals Dan, and addr is the address of the account that deployed the contract. It starts with capital A, B8. Capital A, B8. Now, let's change the struct. So, the new age, 40. Name will be Paul. And I'll paste a random Ethereum address. Let's take the address of this account. You can write the address between double quotes. And I'm clicking Change Instructor. The transaction was executed successfully, and I want to see the new struct value. And it was changed. See the new values. So I've shown you how to declare, initialize, and change a struct variable. Let's go ahead and talk about enums. Enums are one way of creating a user-defined type in Solidity. They are explicitly convertible to and from all integer types, but implicit conversion is not allowed. By the way, the word enum stands for enumerate. Enums are especially useful when we need to specify the current state or flow of a smart contract. For instance, if a smart contract needs to be turned on in order to be ready to accept deposits from users. So let's create a new user-defined type. The syntax is the same as in C language. I'll declare it in the contract, but enums can also be declared at the file level outside of a contract. So, enum, the name of the new user-defined type, let's say state, and a pair of curly braces. And between curly braces, open, closed, and unknown. Note that you don't need to end an enum with a semicolon. Think of enums as user-defined types that contain human-readable names for a set of constants called members. And I'm declaring a new public state variable of type state. Let's say state, the type, public, academy state. And I'm initializing the variable this way, state.open. And in the change instructor function, I'll test the academy state variable before modifying the instructor's data. So I'm changing the instructor's data only if the academy is open. So here I'm writing if academy state equals state.open. A pair of curly braces, and I'm indenting this code. So the code below the if statement. Okay, that was the syntax. We'll use enums in every smart contract we'll develop, so you'll have the opportunity to dive deeper into them. Let's go ahead and talk about mappings. If you are coming from other programming languages, a Solidity mapping is similar to a Python dictionary, a Go map, or a Java hash map. Let's discuss the properties of mapping variables. It's a data structure that holds key-value pairs. All keys must have the same type, and all values must have the same type as well. The keys cannot be of types mapping, dynamic array, enum, or struct, but the values can be of any type, including mapping. A mapping is always saved in storage because it's a state variable. Even though you declare mappings inside functions, they will be saved in storage as well. The mapping's advantage is that lookup time is constant, no matter of size. This is in contrast to arrays that have linear search time. Also note that a mapping is not iterable. We cannot iterate through a mapping using a for loop. The keys are not saved into the mapping because it's a hash table data structure. To get a value from the mapping, we provide a key. The key gets passed through a hashing function that outputs a predetermined index that returns the corresponding value of the mapping. And if we want the value of an unexisting key, we get the default value for that type. Let's go to coding. I'm creating a new smart contract for an auction. In fact, this will be one of the hands-on projects of this course. So contract auction. Ultimately, the users will bid an ETH value for a product or service, and the highest bidder will win. So we have to store both the address of the bidder and the value he or she bid. So I'm declaring a new public variable of type mapping called bids. So mapping and a pair of parentheses. To declare a mapping, use a pair of parentheses after the mapping keyword and between parentheses the type of the keys, in this case address, an arrow using the equal and greater than signs, and the type of the corresponding values, int. The variable will be public and its name will be bids. So our mapping will have the keys of type address and the values of type uint. The values will be the amount of way sent by each address to the contract. There are multiple ways for a smart contract to receive Ether and have an Ether balance. We'll dive deeper into this later in this course, but for the moment, just remember that one way is to define a function with the Payable function modifier. If there's a Payable function, a user can send Ether to the contract by calling that function, and the Ether sent will be added to the contract's balance. So I'm declaring a function called bid. Function bid. This function is payable and public. Payable is a function modifier, a keyword of the language, and public. One more time, remember that payable provides a mechanism for the contract to receive funds in Ether. And inside the function's body, I'm adding bids, the mapping of msg.sender, the address of the account that calls the function equals msg.value. Let me explain to you this line of code. msg.sender is the address that calls the function in a transaction, and msg.value is the value in way sent when calling the function. Both msg.sender and msg.value are global predefined variables in Solidity. So in fact, I'm adding the key pair address value to the mapping, or the address that calls the function and the value sent are added to the mapping. Let's deploy the contract. At the beginning of the lecture, I've said that if you request the value of a non-existing key, the mapping will not give an error saying key not found, but will return the default value for the value type. So, if I take any Ethereum address and paste it in the getter function that was automatically created here, it will return 0, which is the default value for the uint type. I'm visiting etherscan.io and taking the address of the miner that mined the last block. I'm copying it to clipboard. And I'm pasting it in Remix in the bids getter function. And I'm clicking bids. And it returned 0. You can also think of it as a mapping variable that already contains any possible key with the default value for the type 0 in this case. Now, using the first account, I'm calling the bid function and sending 1000 way. I'm entering 1000 in the value field and clicking bid. And the transaction was successful. Now I want to check the value of the key that is the address that has sent the transaction in the mapping. I'm copying the address and pasting it in the bids field. And I'm clicking bids. And the value of the address is 1000. If I select another account and send another value, I'll get a similar result. I'm taking this one, I'm copying it to clipboard, sending 44 and bid. And I'm pasting the address in the bids field. And the value is 44. The value of way sent to the contract by calling the function. Mappings are so efficient in storing and looking up for a value of a key that almost every smart contract uses them. We are almost done with the Solidity data types. Before moving on to other core concepts, I want to do a short recap of storage versus memory, which is a big Solidity gotcha. This is not always intuitive, and having a good understanding of storage versus memory is really important. So I'm creating a contract simply called A. And I'm declaring a public dynamic array of strings. So string, a pair of square brackets, public cities, and I'm initializing it with two values, Prague and Bucharest. Now, I'm creating a function that will try to modify the dynamic array using a memory variable. So function f_memory public. And I'm declaring a dynamic array of strings of type memory. So string memory s1 equals cities. I'm initializing it with the state variable. This variable, s1, will be stored in memory, not in storage, and is initialized with the state variable called cities. So s1 equals cities. Note that it's mandatory for an array, string or struct, to specify memory or storage. If I'm writing string s2, I'll get an error. Data allocation must be specified. And I'm changing the first element of the array, s1 of 0, the element at index 0 equals Berlin. Next, I'll create a similar function, just that the variable s1 inside the function will be declared of type storage, storage being the location where it will be saved. In fact, I'm copying the code to clipboard, pasting it below, and changing it. So f storage, and the s1 is of type storage. Note that in each function, I've changed only the variable defined inside the function and not the state variable defined at the contract level. I'm deploying the contract. And I'm getting the values of the array using indexing. The first element, Prague, and the second element, Bucharest. Now, I'm calling the first function the one that used the memory variable, f_memory. There's no error, and I'm checking the array again. I'm checking if it has changed the state variable. The first element, Prague, and the second element, Bucharest. The state variable, cities, was not modified since the first element of the dynamic array has remained unchanged. It wasn't changed to Berlin. So the function worked on a copy, not on the state variable, on the original one. Now, I'm calling the second function the one with the storage variable, f_storage. There's no error, and I'm checking the contents of the array. The first element, Berlin, and the second element, Bucharest, as expected. We notice that the function changed the state variable even though inside it I've only changed s1 that was defined inside the function. I didn't touch cities. So, s1 is a reference to the same memory location where the state variable was saved, and changing it also changes the state variable. You've already noticed this warning that says function state mutability can be restricted to view. That's because the function doesn't change the blockchain or the state variables that are saved on it. In this lecture, we'll discuss Solidity global variables. There are special variables and functions which always exist in the global namespace and are mainly used to provide information about the blockchain or are generally used utility functions. In a previous lecture, we've already seen two such variables, msg.sender and msg.value. So what is MSG? MSG contains many other members, each of them being a variable on its own, and they are probably the most important global variables. The members of MSG contain information about the account that creates and sends the transaction, and also about the transaction or call. The first member is msg.sender, and it's the address of the Ethereum account, person or contract that is currently interacting with the current smart contract. Interacting with the contract means deploying it or calling a function of the contract. So let's go to Remix and see msg.sender. I'm declaring a state variable of type address called owner. This will be the owner of the contract. Address, public, owner. And I'm declaring the constructor to initialize the owner. Owner equals msg.sender. This means that owner equals the address of the account that deploys the contract. msg.sender is the account that deploys the contract. That account will in fact automatically or explicitly call the constructor. I'm testing it. I'm selecting the first account and I'm clicking deploy, and now I want to see the owner, and this is the owner. The address starts with 5B38 and so on. It's the address of the account that has deployed the contract. msg.sender changes for every function call. So the next time when a function of the contract will be called, msg.sender will have another value. To show you this, I'm creating a setter function called changeOwner. Function changeOwner public. And inside the function, I'm writing owner equals msg.sender. And I'm deploying the new instance of the contract. I'm selecting the first account, I'm clicking deploy, it was deployed, and if I check the owner, it will be the first account or the address of the first account. Now, selecting another account, let's say the second one, I'm clicking change owner. So the second account will call this function, and I'm checking the owner. And it was changed to the address of the second account, the one that called the function. Let's move on to the second global variable called msg.value. A contract can have an ETH balance just like an externally owned account. At the beginning, when the contract is deployed, the balance is 0. If we want the contract to have a positive balance, someone needs to send in a transaction Ether to the contract. msg.value is the amount of Wei sent with a message to the contract. I'm declaring a new state variable that will store the amount of Wei sent to the contract in the last transaction. uint public send value. And I'm declaring a new function called sendEther that can be called when someone wants to send ETH to the contract. Function sendEther. The function is public and payable. A function that receives ETH must be declared payable using the payable keyword. And inside the function, I'm writing send value, the state variable, equals msg.value. This means that sent value is the value of Wei sent with the transaction. As I've already said, a contract account can have an ETH balance as well. Let's return the balance of the current contract. function getBalance. Public view, it doesn't modify the blockchain, returns uint. The balance is the value of Wei as a uint variable. And inside the contract, I'm writing return address of this dot balance. Of course, it's returns, not return. The keyword this in this line of code is the current contract explicitly convertible to address, and balance is a member of any variable of type address. So in fact, it will return the balance of the address of the current contract. Let's test it. I'm removing the other deployments. I'm selecting the first account and I'm deploying it. Perfect. Now, the same account will send a value of Wei to the contract by calling a function. Let's say 5,000. And I'm clicking send Ether. Let's see the balance. And the balance is 5,000. Now, I'll choose another account, a random one, and send another value, 2,000. Now, the balance is 7,000 Wei. I've just shown you how to send Ether to a contract and how to return the balance of the contract. Let's go ahead and take a look at other global variables and functions. GasLeft returns the remaining gas that can be used by the transaction. You can measure the gas used in a block of code by calculating the difference between gas left at the start and gas left at the end of the block of code. Let's see an example. I want to check how much gas a block of code consumes. So function, how much gas? Public view returns uint. Uint start equals gas left. So the gas left at this point. And I'm doing a for loop. I'll do some calculations. So uint j equals 1 and the for uint I equals 1, I less than 20, I plus plus. And inside the for loop, I'll do j star equals I. And after the for loop, I'm taking in another variable the gas left, uint and gas left. And I'm returning the difference. So return start minus end. I'm deploying the contract. And I'm calling the function how much gas. And it returned this value. So the block of code of the function consumed 7,604 units of gas. This doesn't take into account the constant cost of a transaction, which is usually approximately 21,000. Other useful global variables are the members of the block variable. I've already created this very simple smart contract that only declares some state variables which are initialized with some Solidity global variables. I'm deploying the contract and calling the getter functions that were automatically created to see what were the values of the global variables. Let's see the value returned by block.timestamp. So I'm clicking this moment. And it returned the current date and time in the form of the Unix timestamp. That is the running total of seconds since the Unix epoch that was on January 1st, 1970. You can convert this timestamp to human date and time easily. To show you this, I'm searching on Google for Unix timestamp converter and visiting the first link. And I'm copying the timestamp to clipboard and pasting it into the edit box. Copy, and I'm pasting it here. And I'm clicking convert. And this is the current date and time. It was 2 minutes ago. As a side note, many smart contracts rely on block.timestamp or block hash as a source of randomness. Both the timestamp and the block hash can to some degree be influenced by miners, so use them carefully. Let's see the block number. Block number is the number of the current block. If you deploy the contract on the main Ethereum network, you'll see the real block number. Here in Remix, the JavaScript virtual machine runs its own memory blockchain and the block number always starts from 1. Block difficulty is the difficulty of the problem that miners must solve to find a block. This is the proof of work difficulty. And finally, the block gas limit is the current block gas limit. Remember that Ethereum has a block gas limit rather than a block size, like Bitcoin has. Block.gas limit defines the maximum block size. That's all about global variables. Thank you. Any contract has its own 20 byte size unique address that is generated at deployment. The contract address is generated based on the address of the account that deploys the contract and the nonce of the account, which is the number of the transactions that account has sent. The contract address cannot be calculated in advance. Address is a variable type in Solidity. Note that there are two types of addresses, payable and non-payable or plain. The idea behind this distinction is that address payable is an address you can send Ether to, while a plain address cannot have Ether sent to. An address has the following members: balance and the functions transfer and send only for the payable addresses. There are call, delegate call, and static call as well. Let's move ahead and talk about the balance of a contract and payable functions. A smart contract can have an ETH balance just like an externally owned account. A contract receiving ETH must have at least one payable function. And the contract receives ETH in multiple ways. One way is simply by sending ETH to the contract address from another account. In this case, the contract must have at least one of the following functions: receive, which is external and payable for empty call data and any value, and fallback, which is external and payable as well when no other function matches, not even the receive function. And the second way to receive ETH is by calling any payable function and sending ETH with that transaction. Let's go to coding. I'm creating a contract called deposit. And I'm declaring the receive function to receive Ether. So receive, this is a keyword, external, payable. This was introduced in Solidity 0.6, and the contract can have only one receive function declared with this syntax, so without the function keyword. The function executes on calls to the contract with no data, such as simple ETH transfers from externally owned accounts or calls made via send or transfer address functions. Note that the function cannot have arguments, cannot return anything, and must have external visibility and payable state mutability. I'm also declaring a fallback payable function that is called when msg.data is not empty, like for example, when no other function matches. So fallback, external payable. Note that if I deploy the contract without any of these two functions and someone sends ETH to the contract, the transaction will fail. I'm also declaring a function that returns the balance of the contract. Function getBalance. Public view returns uint. And inside the function, I'll have return address of this dot balance. This is the current contract, explicitly convertible to address, and balance is a member of any variable of type address. So it will return the balance of the current contract. And I'm deploying the contract on Ring-B testnet. Note that you need MetaMask and an account with some ETH to pay for the gas. I've shown you in the first section of the course how to install MetaMask and how to get fake ETH for the Ring-B testnet. I'm selecting Injected Web3. MetaMask is popping up and I'm entering the password to unlock it. I'm clicking Next, Connect, and it's connecting to Remix. It says here, connected. The first account is connected. And I'm deploying it. A new window is popping up, and I can set the gas price. I'll set it to 3 gigawatt. And I'm clicking Confirm. The transaction was sent, and these are the transaction's details on Etherscan. And the transaction was already confirmed. I can refresh the page. It was included in this block. It will be reflected in a short while. There are already 2 block confirmations. This is the contract's address, and I'm copying it to clipboard. Remix has already loaded the contract, but I can paste the contract's address here as well. Note that Remix is a web interface to the contract, and in order to interact with it, you need the ABI, so the contract's abstract binary interface. So you can load it in Remix only if you have the source code. And in Remix, I'm clicking Get Balance. And as expected, the balance of the contract is 0. Now, from another account, I'm sending ETH to the contract's address. To make it more interesting and show you different ways, I'm gonna use my Ether wallet. I already have an account and I'm unlocking it. Its balance is 1.5 Ring-B ETH. I'm copying the contract's address to clipboard and I'm sending a transaction. Don't forget to select the Ring-B network in the network page here. By default, my Ether wallet connects to the main Ethereum network. I'm sending 0.5 ETH and I'm pasting the contract's address. And I'm clicking Send Transaction. And confirm and send. And I'm checking its status on Etherscan. The transaction is still in the transaction pool and is in the pending status. Great, the transaction has already been included in a new block. The transaction was confirmed, and I'm returning to Remix, where I'm calling the getBalance again. And we see the balance of the contract in Way. This value is 0.5 ETH in Way. Note that this contract keeps all Ether sent to it with no way to get it back. Take it as just an example and don't use it on the mainnet because you'll lose real money. Okay, let's see the second way a contract can receive ETH, and that's by calling a Payable function and sending it to the contract. I'm declaring a new function. Function send Ether, public, and Payable. The function's body can be empty, or you can add code as well. For example, you int x, x++. Take it as an example. And I'm deploying the new contract on Ringby. It's already connected to MetaMask, and I'm clicking deploy. MetaMask is popping up, I'm clicking confirm, and I'm waiting for the transaction to be mined. This is the transaction's details on Etherscan. The transaction was confirmed, so the new contract was deployed. I'm returning back to Remix. Just to be sure that it loads the right contract, I'm copying the address to clipboard and pasting it in @address here and click @address to load the contract. So the last contract is the second one in the deployed contracts panel. At the moment, its balance is 0. Now, I'm sending a random value of Way to the contract by calling the send Ether function. I'll use the same account that I've used for deployment. I'm clicking send Ether. The MetaMask is opening up. I'm clicking confirm. And I'm waiting for it to be mined. Okay, it was already mined, so I can get the new balance of the contract. I'm clicking get balance. And its balance is the exact value of Way I have sent. Just one final remark. When we called the send Ether function by clicking send Ether, we've created a transaction and sent it to the contract address. The transaction was sent from this account, an externally owned one, to the contract's address. The function and its arguments are found in the transaction's input data, so here, which practically tells the contract what function to execute. This is the function and its arguments. If you take a look at input data at the first contract, you'll see that it's empty. In that case, I sent Ether directly to the contract's address. So I didn't call a specific function of the contract. That's all. This is an important section, so take your time to deeply understand all the concepts presented here. In the last lecture, we've seen how to send Ether to a contract. We've talked about the receive and fallback functions. Now, let's see how to access the contract's balance or how to send the ETH stored in the contract to another account, a contract, or an externally owned one. I'm declaring a function that will transfer ETH from the contract to another account. So function transfer Ether. The function will have two parameters, the recipient's address and the amount. So address, payable, recipient. And uint amount. When someone will call the function, this amount of Way will be sent to this recipient address. The function is public and will return a Boolean value. First, I want to check if the amount that will be sent is less than or equal to the contract's balance. So if amount less than or equal to getBalance, the function that returns the balance. And I'm calling the transfer function of the payable address. So recipient dot transfer of amount. It will transfer the amount from the current contract's balance to the recipient's address. And I'm returning true. And else, I'm returning false. Great. I'm deploying the new contract on Ringby. MetaMask is already connected to Remix, so I'm clicking Deploy. And confirm. I'm waiting for it to be confirmed. Great. The transaction was confirmed and the contract was loaded into Remix. It's a new contract, so its balance is 0. I'm copying the contract's address and I'm sending some ETH to it. I'll use MetaMask. Send. I'm pasting the address. I'm sending 0.2 ETH and I'm clicking next and confirm. By the way, the receive function will be automatically called. The transaction was already confirmed and we see the correct value when I click the getBalance function. This is 0.2 Ether in Way. Now, I'll send half of the contract's balance to a random Ethereum account. I'm choosing as the recipient the second account that is present in MetaMask. This one. I'm copying it to clipboard, pasting it here, comma, and the value I'm gonna send. I'm copying it, the entire balance to clipboard, and changing 2 to 1. I'm sending half of the balance. I'll run the transaction from the first account, so I'm selecting the first account back in MetaMask. And I'm clicking Transfer Ether. And it's done. I'm checking the balance of the contract. It was changed accordingly. If I check the account on MetaMask, I'll see that it has received the funds. So it was funded with 0.1 ETH. We can see details about the transaction on Etherscan as well. See how the contract has transferred 0.1 Ether from X address to this account, the second account shown in MetaMask. Great, it worked just perfectly. However, this approach has a major security drawback. Anyone in the world can access the contract's balance and send to his own address or to a random one the entire contract's balance. We are taking a short break, and in the next lecture, I'll show you how to protect the contract's balance against unauthorized access. I've just shown you how to transfer the balance of a contract to another account. We use the transfer function, one of the members of any payable address. The payable address will receive the amount of Way that is given as an argument. With this approach, there's a big security issue because anyone could call the function and transfer the entire balance to his own address or to one that he controls. And with ETH valued at thousands of dollars, this is really serious. So we need to protect the contract balance in such a way that only the owner of the contract can transfer it to another address. One approach is to declare and register the owner of the contract and then check that the account that calls the function transferring it is the owner. So in fact, we are restricting the access to this function, to the transfer function, to the owner only. I'm declaring a new variable of type address called owner. Address, public, owner. And I'm also declaring the constructor to initialize the owner with the address of the account that deploys the contract. So the one that creates the contract is the owner and will have full access to the contract's balance. So constructor owner equals msg.sender. The next step is to add a condition that limits the access to the transfer ETH function to the owner. You could use a classical if statement that checks that the address that calls the function is the owner and return false if it's not. Also, you could use the require function, which is the idiomatic way in Solidity to check for conditions and throw an exception if the condition is not met. So, at the beginning of the function's body, just after the opening curly brace, I'm adding require owner equals msg.sender. The argument of require is a Boolean expression or condition that returns either true or false. If it returns true, the function execution continues with the rest of its body. But if the condition returns false, like in the case the address saved at deployment in the owner variable is not the same as the address that calls the function and transfers money, an error is created and the transaction fails. By the way, you can optionally provide a message string for require as the second argument. Like this. Transfer failed. You are not the owner. So, require is a built-in function that checks the validity of conditions that cannot be detected before execution. They are contract state variables or return values from calls to external contracts. Let's check the contract. I'm deploying it on Ring B using Remix and MetaMask from the first account that is available in MetaMask. This is the first account. And I'm clicking deploy, a new window is popping up, I'm clicking confirm, and I'm waiting for the transaction to be confirmed. It was confirmed, and the contract was loaded in Remix. Now, I'm sending 0.5 ETH to the contract. Any account can send ETH to the contract, and I'm gonna use the first one. I'm copying the contract's address, I'm opening MetaMask, send, I'm pasting the contract's address, writing 0.5 in the amount box, and clicking next and confirm. The transaction was confirmed, and I see the balance of the contract. This is 0.5 ETH in Way. Now, I'll try to transfer some amount of Way from the contract to another account, and I'll call the transfer ETH function from another account, not the owner. I'm opening MetaMask, I'm selecting the second account, which is not the owner. Pay attention that it needs a positive balance to pay for the gas. Okay. So this account will run the transaction. I'm pasting here an address. For example, his own address. It could be any address. and an amount of way. A random amount of way. It doesn't matter too much. And I'm clicking Transfer Ether. Remix is warning us that the transaction could fail, but I'm sending it anyway. See that the transaction will be executed from the second account, which is not the owner. The owner is the first account of MetaMask. And I'm clicking Confirm. And I'm tracking the transaction on Etherscan. It has already failed. Let's see the message on Etherscan. The status is fail with error, transfer failed, you are not the owner. So another account couldn't access the contract's balance. Now, let's transfer some ETH from the owner account. I'm selecting the first account, which is the owner, in MetaMask. And I'm calling the same function, transfer ETH, from the owner account. It doesn't matter the recipient address or the value sent. I just want to call the function. The transaction will be executed from the first account, from the owner, and I'm clicking Confirm. And I'm tracking it on Etherscan. I'm waiting for the transaction to be confirmed. And it was confirmed. I'm refreshing the page. And the status of the transaction is success. The owner could transfer it from the contract's balance to another account. Hello guys! It's time to start our first smart contract, which will be a decentralized lottery. We'll focus on Solidity backend programming and Ethereum core concepts, not on the frontend or JavaScript programming. This will be a complete and working decentralized lottery application, so let's get started. The earliest mention of lottery games was in China during the Han Dynasty in around 200 BC. There was a game called Kino, and you can actually still find it in many Asian casinos. These lotteries are believed to have helped to finance major government projects like the Great Wall of China. The idea of the lottery is simple. The organizer is collecting money from players, and then a randomly selected player called the winner is getting rewarded, while others are losing all their money. Let's take a closer look at our lottery algorithm. After deploying the contract, anyone will be able to send a fixed amount of Ether directly to the contract's address, and the address of the sender will be registered in a dynamic array called players. A user can send as many transactions as he wishes in order to have more chances of winning. We'll consider the fixed amount of ETH someone could send into the lottery as being 0.1 ETH. In fact, it's the same principle as in a classical lottery where you can buy as many tickets as you want at a fixed price per ticket. There will be a lottery manager as well. This will be the account that deploys the contract. If there are at least 3 players, the manager could pick a random player from the players list that will be the winner, and the entire contract's balance will be transferred to that winner's address. At this point, the lottery will be reset and ready for the next round. And that's all. We are taking a short break, and in the next lectures, we'll implement all the lottery features step by step. Let's get started by declaring the contract's state variables. Anyone can enter the lottery simply by sending Ether to the contract's address. We'll save the address of those who send Ether to our contract and enter the lottery. We don't know exactly how many people will send Ether to the lottery, so we'll declare a dynamic array called players. There could be 10, 50, 100 or more players. So I'm declaring a dynamic array of type address, and the elements of the array will be the players' addresses. Address, Payable, a pair of square brackets, public, and players. The array is public, so it could be easily accessed from external applications. Anyone will be able to see the contents of the array. One of the players in the array will be the winner and will receive all the funds. That's why I declare it as being composed of payable addresses. I remind you that there are 2 types of addresses, payable and non-payable. The idea behind this distinction is that only a payable address is an address you can send Ether to, while a plain address cannot have Ether sent to. The lottery will also have a manager, which is the externally owned account that deploys the contract, starts the lottery, picks the winner, and resets it for the next round. So address, public, manager. Now, let's define the contract's constructor that will be called only once at contract creation and will set the manager to the address of the account that deploys the contract. So constructor, a pair of parentheses, and a pair of curly braces. And inside the constructor, I'm writing manager equals msg.sender. I remind you that msg.sender is a global variable in Solidity that holds the address of the account that's interacting with the current contract, and in this case, it means creating the contract. So the manager, which is an address, will be the address of the person that deploys the contract. the constructor will be called only once, so there's no possibility to change the manager without declaring a setter function that modifies the variable. Okay, that's all for the moment. We've declared the contract's state variables and constructor. In the next lecture, we'll see how someone can enter the lottery. We've declared the contract's state variables and constructor. Now, we'll see how someone could enter the lottery. A user enters the lottery simply by using a wallet to send 0.1 Ether to the contract's address. The user's address will be added to the dynamic array called players, and the sent amount will be added to the contract's balance. In the previous section, when we've discussed the Solidity programming language, we've seen that a contract can receive ETH if there's either a function called receive or another one called fallback. So I'm declaring the receive function for the contract to receive Ether. Receive external payable. As a short recap, I want to tell you that this was introduced in Solidity 0.6, and a contract can have only one receive function declared with this syntax. So without the keyword function. The function is run automatically when the contract receives ETH from externally owned accounts. Note that the function cannot have arguments, cannot return anything, and must have external visibility and payable state mutability. Inside the function, I'll add the address that sends ETH to the player's array. So I'm calling the push function, which is a member of any dynamic arrays and adds an element to the array. So players.push of msg.sender. Note that the players array consists of payable addresses, so I have to convert msg.sender to a payable address before pushing it to the array. So I'm writing payable and msg.sender between a pair of parentheses. This is how you convert a plain address to a payable one. Now, there are no errors. Now the contract can receive ETH, and the one that sends ETH is added to the player's array. The next step is to create a function that returns the contract's balance in way. Function getBalance. Public view returns uint. And inside the function, I'm writing return address of this dot balance. I've already discussed this in the previous section, so I won't dive into it again. Okay, let's test this contract. There are no compilation errors, and I'm deploying the contract using JavaScript VM and the first account. The contract was deployed. This is the instance. Normally, an externally owned account will send ETH to the contract's address using a wallet such as MetaMask or MyEtherWallet. We'll do that as well later on when we'll deploy it on Ringbit testnet. For the moment, I'll test it using Remix. I'm selecting an account, setting the value of way I want to send to the contract, and then clicking the Transact button, the one down below in the Deployed Contracts side panel, this one. The receive function was automatically called, and this is the same as sending ETH to the contract's address using a wallet. And I'll do the same using other two accounts. The first one, I'm sending a value of way, a random one. And another one. let's see the balance of the contract. I'm clicking Get Balance. And this is the balance of the contract in Way. Let's check the players. This is the first player at index 0, the second player, the third one, which is also the last player. If I try to get the next player, I'll get an error. There are only 3 players in the array. We'll stop here, and in the next video, I'll show you how to use require to validate the user's data and test for different conditions. Let's go ahead and see how to validate the user's data and how to test for different conditions in Ethereum smart contracts. We'll require every user to send into the lottery the fixed amount of 0.1 Ether. Each transaction will give the user a chance to win the lottery, so it's logical that everybody sends the same amount. Of course, if the user wants to have more chances, he can send more transactions to the lottery contracts. The code that implements this functionality will be added in the function called receive, because that's the one being executed when an account transfers ETH into the contract. We could use an if-else with a return statement, but the Solidity idiomatic way to test for such conditions is to use require. This is a built-in function that checks for conditions and throws an exception if the testing condition returns false. So, at the beginning of the receive function, I'm adding require msg.value equals and the value of 0.1 Ether in Way. I'll use the online converter we've seen in the other lectures. So 0.1 Ether is this large value in Way. I'm copying it to clipboard. And I'm pasting it here. Let's talk a little bit about Ether units. Ether numbers without a suffix are assumed to be Way. In this case, there's no suffix, so it is assumed that they are Way. However, this is not very readable. You can easily add a 0 and you'll get another number without noticing it. It seems it's the same number, but it's not. So, there's the suffix of Way, gway or Ether, to specify a subdenomination of Ether. I'm changing this value, which is the equivalent in Way of 0.1 Ether, to this one, 0.1 Ether. And it's the same. And I'll remind you that msg.value is a global variable that represents the value of Way sent to the contract in a transaction. So what does this statement mean? If the value sent to the contract is not equal to 0.1 Ether, an exception, which is a runtime error, is thrown and the transaction will be reverted to the initial state. Note that the transaction will consume all the gas till the require function. So, if there's any piece of code before require, that code will consume gas. uint I equals 1, I++. This code will consume gas. That was the first condition. The second one will be that only the manager can see the balance of the contract. That's why before returning the balance of the contract, I'm adding require msg.sender equals manager. I've already explained require, so I'm just saying that if another account, not the manager, calls the getBalance function, the condition of the require function evaluates to false and the transaction fails. Let's deploy and test the new contract. I'm deploying it using the first account. This will be the manager. The address starts with 5B38. This address. Now, I'll try to send a value different than 0.1 Ether to the contract. For example, I'm sending this value of way. And there's an error. A player must send exactly 0.1 Ether. I'm copying this value to clipboard, which represents 0.1 Ether, and I'm sending that exact value. And there's no error. Transaction mined and execution succeed. This is the balance of the contract. Let's try the second condition. I'm selecting another account, for example the second one, and I'll try to call the getBalance function. And I've got an error. Only the manager can see the balance of the contract. Let's see how to select the winner of the lottery. After at least 3 players have entered the lottery, the manager can randomly select a winner. There are more approaches, and one of them is to calculate a random index of the dynamic array that holds the players, and the player at that randomly calculated index will be the winner. Let's dive deeper into this and do some tests in a JavaScript console. First, I want to introduce the modulo operator, which returns the remainder of a division operation. In JavaScript, the percentage symbol is the modulo operator. For example, the expression 5 mod 2 would evaluate to 1 because 5 divided by 2 has a quotient of 2 and the remainder of 1. While 19 mod 5 would evaluate to 4 because 19 divided by 5 has a quotient of 3 and the remainder of 4. To select the winner of the lottery, we'll calculate a very big random integer number and then the remainder of the division between that very big random number and the length of the array. Something like this. Let's suppose this is the big random integer and the players array has a length of 8. So I'll do this number, mod 8, and I've got the remainder as being 7. So the player at index 7 is the winner. Let's try another one. Now, this is the big random number and there are 21 players. So, the random number, mod 21, and I've got 18. The player at index 18 will be the winner. Note that the remainder will always be less than the players in the array, so it will be a valid index. We'll take a short break, and in the next lectures, we'll talk about random numbers in Solidity, selecting the winner and sending the funcs to his address. Generating truly random numbers in Solidity is difficult. There isn't a dedicated function that returns random numbers, and even if it was, like in other programming languages, those numbers would only be pseudo-random because no language is capable of generating completely random numbers. In this smart contract, we'll use the classical way of generating a random number in Solidity. Consider it just as a proof of concept and don't use it in applications that involve real money because there's the chance you'll get hacked. So, we'll create our own function called random that will return a very big pseudo-random integer. Function random public view returns uint. We declare the function as being public to be easily called from Remix, but it can be internal as well. And as I said, it will return a random uint number. Now, we'll call the CakeShack256 function that will compute the hash of the input using CakeShack256 hash algorithm. This function takes a single argument of type bytes, and since I want my random number to be computed based on more random values, I'll call another function called abi.encodePact. So abi.encodePact, and the function will perform pact encoding of the given arguments and return a variable of type bytes. And the function's arguments are block.difficulty, block.timestamp, and players.length. Block.difficulty is the proof of work difficulty of the current block. Block.timestamp is the Unix timestamp of the current block, and players.length is the number of players in the array. The blockchain is constantly growing, so all these values will be random for each call, and we can assume that this will result in a random number just good for our lottery. I'm converting the result to uint and then returning it. So return uint of this expression. Let's test the function. I'm deploying the contract and testing the function after adding a few players to the players array. Each player should send exactly 0.1 ether in way, so this value. I'm copying it to clipboard. And this is the first player. The second player. And the third player. There are 3 players in the array. And I'm calling the random function, and I notice that each time it returns a different big unsigned integer. Pay attention that this function cannot be used in a decentralized lottery that has access to a large amount of ETH because it doesn't return a truly random number. The miners have the choice to publish a block or not. If they mine a block that they don't like, they can throw it out. Let's suppose a miner signs up for a decentralized lottery for 1000 ETH, and the winning lottery depends on the block hash. The miner will just keep mining blocks and not publishing them till he gets the block he wants. And he's incentivized to do so since the win worth ether values of millions. A random number system needs to be strong enough that even if an attacker knows exactly how you are creating the random numbers, the system remains unpredictable. A truly random number generation in Solidity must be done by sending a seed to an off-chain resource like an oracle, which must then return the generated random number and verifiable proof back to the smart contract. In smart contracts, the recommended way of generating random numbers that deal with large amounts of ether is to use something called Chainlink VRF. This is not within the scope of our course, but I'll attach an external resource to this lecture so you can dive deeper into it. Let's go ahead and declare a function that picks the winner and transfers the entire contract's balance to the winner. So, function pick winner public. To test that the function works well and picks a random player, I'll just return the address of the winner for the moment. And when I'm sure that everything works as expected, I'll transfer the funds to the winner. So I'm adding view returns address. The first statement of the function will check if the account that calls it is the manager of the lottery. I want only the manager to be allowed to pick the winner and transfer the lottery's money to the winner's account. So require msg.sender == manager. If another account tries to pick the winner, the transaction will fail and all changes to the blockchain will be reverted. And I'm requiring the presence of at least 3 players in the lottery before one of them can be selected as being the winner. So require players.length greater than or equal to 3. Next, I'm declaring a local variable called r that will be the big random number we've talked about in the last lectures. It will be used to select a random player from the dynamic array. So uint r = random. I'm calling the function we've declared. I'm also declaring a local variable of type payable address that will be the winner. So address payable winner. Now I'll select the winner the way I've explained to you in the last lectures by selecting a random index of the array as the remainder of the division of that big integer by the length of the player's array. So uint index = r mod players.length. And the winner is the address of the array at that index. So winner = players of index. And I'm returning it. Let's test the function up to this point. The first account will deploy the contract and will be the manager. Now, using 3 or 4 different accounts, I'll send 0.1 Ether to the contract. The first player, the second player, the third account will be the third player, and the last player, a random account. Okay, there are 4 players in the lottery. And I want to pick the winner by calling the pick winner function. I've got an error because the function was called by another account, not the manager. So I'm selecting the first account, which is the manager, and calling the function again. I'm clicking pick winner. And this is the address of the winner. I'm clicking it again, and I've got another address. And again, and I've got another random address, and so on. So the function returns a random address and passes the test. Now, I'm changing the function to transfer all the lottery funds to the winner. So I'm removing view and returns. The function will change the blockchain, so it cannot be a view function. And I'm removing the return statement as well. And I'm adding winner.transfer of getBalance, the function that returns the balance of the contract. I remind you that transfer is a member function of any payable address, and it will transfer the amount of way given as argument to the payable address, winner in this case. And that's all. I'm deploying and testing it again. The first player is entering the lottery. The second player is entering the lottery as well. This will be the third player. And the last one. There are 4 players in the lottery. I'm selecting the manager account and I'm clicking Pick Winner. The transaction succeeded and a random winner received all the money. So this account is the winner. Look at its balance. It's almost 100.3 Ether because it received 0.4 Ether. It's not 100.3 because it had to pay for the gas as well. After selecting the winner and transferring the lottery's funds to the winner's address, we must reset the lottery to be ready for the next round. We'll simply do that by resetting the player's dynamic array. So, after we transfer the contract's balance to the winner, we'll initialize the player's state variable to an empty in-memory dynamic array. So players equals new address payable, a pair of square brackets, and a pair of parentheses and 0 between parentheses. 0 means the size of the new dynamic array of type payable address. So this will reset the lottery. Let's deploy and test the contract. The first account is deploying the contract, and the 3 players are entering the lottery. Okay, there are 3 players in the lottery. I'm selecting the manager account, the first one, and clicking Pick Winner. The winner was selected and is in fact this account. We can see that from its balance. Its balance increased by 0.3 Ether. So the winner was this account and the funds saved in the lottery were transferred to it. Also note that the lottery was reset and it's now ready for the next round. If I try to get the first element of the array at index 0, I'll get an error because the array is now empty. We've just finished programming our first decentralized application, and before deploying it to the Ethereum blockchain, I want to do a short recap. Our lottery smart contract has only 2 state variables, a dynamic array of type address payable and another one of type plain address, which is the manager. We do not know in advance how many players will enter the lottery, and that's why we declare the array as being dynamic. One of them will be the winner and will receive the funds, and that's why the address of the array are payable. Only a payable address can receive Ether. Next, we've declared the constructor that is automatically called when the contract is deployed, and it initialized the manager state variable to the address that deploys the contract. This will have administrative privileges on the lottery. Note that the manager cannot be changed since there's no setter function to change the variable. Next, we've declared the receive function that is necessary for a contract to receive ETH to its address. Each time Ether is sent in a transaction to the contract's address, this function will be automatically called. Note that the function cannot have arguments, cannot return anything, and must have external visibility and payable state mutability. Inside the function, using the push function, I've added the address that has sent ETH to the contract to the player's array. Also, I had to convert msg.sender to a payable address before pushing it to the array because the player's array consists of payable addresses. Now the contract can receive ETH. There's also a condition that requires that the value sent to the contract must be equal to 0.1 Ether. We've also declared a function called getBalance that returns the contract's balance in way. It can be called only by the manager, so this is why I've used the require function. Next, we've created a helper function called random that returns a very big random integer number. The function was declared public to test it in Remix, but you can declare it as being internal as well. The random number is not truly random because it is computed by hashing some deterministic values such as the block difficulty, the block timestamp, and the player's length. A malicious miner could alter these values in such a way that he will win the lottery. Then comes the function that picks the winner and transfers the lottery funds to his address. The function starts with two constraints. Only the manager can call it, and there should be at least 3 players in the lottery before the manager can pick one of them as being the winner. Inside the function, I've declared 2 local variables, r, which is the big random integer, and winner, which is the address of the player that will win the lottery. And I've computed a random index as the remainder of the division of r by players.length. The winner will be the player at that index, and the function will transfer all the money to his address. I've called the transfer member function of any payable address, and the argument is the entire balance of the contract. Of course, in way. And finally, I've reset the lottery by resetting the player's dynamic array. Now the lottery is ready for the next round. That was our smart contract. We are taking a short break, and in the next lecture, we'll deploy it to Ringbit testnet. Now it's time to deploy and test the contract on Ringbit testnet. You'll need MetaMask and an account with some ETH to pay for the gas. I've already shown you in the first section of the course how to install MetaMask and how to get ETH for the Ringbit testnet. I'm selecting Injected Web3 and the MetaMask window is popping up, and I'm unlocking it. Great. It's connected. And there are 2 accounts. I'll deploy the contract using the first account. This will be the manager of the contract. I'm clicking Deploy. MetaMask is popping up again. Account 1 will deploy the contract, and I'm clicking Confirm. And I'm tracking the transaction on etherscan.io. It's pending, and it was confirmed. I'm refreshing the page. It will be reflected here in a short while. Great. The transaction has created a contract, and this is the address of the contract. By the way, the contract's instance was loaded in Remix. Using another Ethereum account, I'll send 0.1 Ether to the contract's address, and I'm using my Ether wallet. I'm unlocking the wallet. Note that my Ether wallet is connected to Ringbit testnet. Pay attention not to be connected to the main Ethereum network. The balance of the account is almost 1 Ether, and I'll send 0.1 to the contract. I'm copying the contract's address to the clipboard. Send transaction 0.1, and I'm pasting the address. And send transaction. Confirm and send. And I'm checking the transaction on Etherscan. Now expanding. I'm waiting for the transaction to be confirmed. It takes a few seconds. Okay, the transaction was confirmed. There should be at least 3 players in the lottery, so I'll send 2 other ETH transactions to the contract from the 2 accounts I have in MetaMask. From the first account, I'll send 0.1 Ether to the contract's address. I've pasted the contract's address, and the amount will be 0.1 ETH. And I'm clicking Next and Confirm. I'm tracking the transaction on Etherscan. And it was confirmed. Now, I'm selecting the second account of MetaMask, and I'll send 0.1 Ether to the contract's address from this account. Next, confirm, and it's done. I want to view the transaction on Etherscan. In a few seconds, the transaction will be confirmed. Now back to Remix, I'm checking the balance of the contract using the manager account. So I'm selecting the first account of MetaMask, that is the manager, and I'm clicking Get Balance. And the balance of the contract is 0.3 Ether in Way. This value represents 0.3 Ether in Way. Good. Let's pick the winner. I'll try this first using another account, not the manager. So I'm selecting the second account in MetaMask. And I'm clicking Pick Winner. Remix knows that the transaction will fail, but I'll send it anyway. I'm tracking it on Etherscan. The transaction will fail because it was executed by another account, not the manager of the lottery. And the transaction failed as I expected. Now I'm trying to pick the winner again, this time using the manager account. I'm selecting the first account, which is the manager, and I'm clicking Pick Winner. And I'm sending the transaction. I'm tracking it on Etherscan. The transaction was executed successfully, and we can see in the transaction input data that the pick winner function was called. I'm clicking the contract's address to see all transactions sent to the contract. You are seeing many transactions because I've made some tasks. Let's see more details about the last transaction, the one that picked the winner. So I'm clicking the transaction hash or ID. And we see that the contract has transferred 0.3 Ether from X address to the address of the winner. This is the address of the winner. The address that starts with 0x3781c3 and so on. This is the address of the first player that entered the lottery. It's the address of the account that used my Ether wallet to send Ether to the contract's address. I'm refreshing its balance, and it's now 1.199. So 0.3 Ether was added to the account's balance. Let's see more information about this account on Etherscan. So I'm copying the address and pasting it on ringb.etherscan.io. And I'm going to internal transactions. The account received 0.3 Ether 5 minutes ago. These internal transactions value transfers that were initiated by executing a contract. Okay, that's all. One final remark. If you get an error when you try to enter the lottery, just increase the gas limit. For example, I'm selecting the first account in MetaMask and I'm sending 0.1 Ether to the contract's address. So send. I'm pasting the contract's address. This is the contract's address. I'm pasting it here in MetaMask. I'm writing 0.1 Ether. And here I'll increase the gas limit to 100,000. And the gas price will be 3 gigaway. Do this if you get an error when you try to enter the lottery. That's all. Thank you. Hello guys and welcome. We'll start developing a new smart contract for a decentralized auction like an eBay alternative. We'll focus only on the Ethereum smart contract and not on the website or the frontend that will be used to interact with it. Let's discuss the parameters of our auction. The auction will have an owner, the person that sells a good or service, and this will be the one that starts the auction, cancels it if there's an emergency, or finalizes the auction after a specific amount of time. Anyone who has an Ethereum wallet can bid by sending Ether while calling a function called placeBid. However, the owner will not be allowed to bid to artificially increase the price. There will be a mapping state variable where both the address of the bidder and the value sent will be registered. Users are incentivized to bid the maximum value they are willing to pay, but they are not bound to that full amount, rather to the previous highest bid and an increment. The contract will automatically bid up to a given amount. This is in fact how most auctions work. If you want to bid for a pair of shoes on eBay and the current price is $50, then you can bid $200, but that doesn't mean that the final price will be $200. eBay will automatically bid for you $1 or a few dollars over the highest bidder to the maximum $200. So you could buy the pair of shoes for $70 even though you've placed a bid for $200, which means you are willing to pay $200. Our auction will have an increment of 100 way. The highest binding bid will be the selling price, and the highest bidder the address of the account that won the auction. After the auction is finalized by the owner will get the highest binding bid and everybody else will withdraw their own amount of ETH sent to the auction. This was a short introduction to our decentralized auction. We are taking a short break, and in the next lectures, we'll start developing our smart contract in Solidity. I'm starting from scratch and creating a new contract called auction. Let's declare the state variables of our auction contract. There will be an owner, the address that will deploy the contract, and to which the highest binding bid will go if the auction completes successfully. So address, payable, public owner. I'm declaring it as being payable and public. Being payable means that it can receive ETH, and being public means that it can be accessed and seen by anyone. For the moment, we don't separate the admin of the auction from the beneficiary of the funds, but we could do that if we wish. Auctions also require both a starting and an ending time. In Solidity, time is very tricky. Block timestamps are set by miners and can be spoofed easily, so it's not safe to use the global variable called block.timestamp. A good practice is to calculate the time based on the block number. I'll explain that to you in detail in a few minutes when we'll declare the constructor. For the moment, I'll declare two variables of type uint called startBlock and endBlock. They will be used to calculate when the auction starts and ends. So uint public startBlock and uint public endBlock. The product or service listed for sale in the auction will also have a description, maybe some images and so on. Saving this information on the blockchain is very expensive, so we'll use another decentralized off-chain solution. We could, for example, save all of the information about the item on IFS or interplanetary file system, and in the smart contract, we'll save only the IPFS hash that uniquely identifies the information. So I'm declaring a new public variable of type string called IPFS hash. String public IPFS hash. By the way, we'll discuss IPFS later in the course. I'm also declaring an enum type called state to save the state of the auction. Our auction can be at any moment started, in the running state, ended, or cancelled. So enum state, and between a pair of curly braces, the states started, running, ended, and cancelled. Don't use a semicolon here. We've discussed enums in the Solidity section. And I'm declaring a state variable of type state called auction state. So state, the type, public, and the name of the variable, auction state. Next, I'll declare a public uint variable called highest binding bid, which is in fact the selling price. Uint public highest binding bid. And the address that wins the auction and pays for the product or service will be stored in another variable called highest bidder. I'm declaring the address as being payable so that the highest bidder can also receive back all the funds if the auction is cancelled or he's outbid. Address, payable, public, highest bidder. Next, I'll declare a mapping variable called bids that will store for each bidder the address and the value sent in the auction. So mapping address equals greater than uint public bids. This is how you declare a mapping variable. The keys are the addresses of the bidders, and the corresponding values are the amounts they have sent. The next state variable will be the bid increment. As I've already explained in the introduction, the contract will automatically bid up to the given amount in steps of this increment. So uint bid increment. These are the state variables of the contract, And now we can move on and declare the constructor. So constructor, and I'm initializing the owner to the address that deploys the contract, and that's msg.sender. Owner equals payable of msg.sender. You have to convert msg.sender to a payable address because owner is declared as being payable. I'm setting the auction state to running. Auction state equals state.running. Next, we'll initialize the auction starting and ending date. As I've already said, we'll use the block number to calculate the time because it is safer. We already know that the Ethereum block time is 15 seconds, meaning that a new block is created and added to the blockchain roughly every 15 seconds. Based on the block time, we can calculate when the auction starts and ends. I'm initializing the start block to the current block because I want it to start right away. You can initialize it to another block in the future if you want the auction to start in the future, knowing that a new block is generated every 15 seconds. So start block equals block.number, the current block. Block.number is a global variable in Solidity. Let's take an example and suppose that the auction must be valid for a week. How many new Ethereum blocks will be generated in a week? First, let's see how many seconds are in a week. 60 seconds in a minute multiplied by 60 minutes in an hour multiplied by 24 hours in a day multiplied by 7 days in a week. So we have this number of seconds in a week. And to calculate the number of new blocks, I'll divide this number of seconds by 15. So in a week, there will be 40,320 blocks generated. So end block equals start block plus 40,320. This means that the auction will be running for a week. Maybe you think that it's strange for the owner, that is an end user, to enter the block number instead of date and time in human format. But this is not a problem at all. The end user doesn't have to know about all these details, such as blocks and block time. It will enter the date and time in human format, and the front-end interface will do all the math and convert that date and time into the format I've shown you. Okay, let's go ahead and initialize the other state variables. IPFS hash equals, and I'm initializing it to an empty string. And the bid increment will be 100 way. Okay, that's all. In the next lecture, we'll discuss function modifiers that will be used in our auction contract. Welcome back. We'll set apart the auction contract just for a moment and talk about a Solidity feature called function modifiers. Function modifiers are used to modify the behavior of a function. For example, you can use a modifier to automatically check a condition prior to calling the function. This way, you avoid writing redundant code. These modifiers are inheritable properties of contracts and may be overwritten in derived contracts. Let's take a look at a practical example. There's this smart contract called property with two state variables, the constructor that sets the owner to the address that deploys the contract, and two setter functions that change the state variables. Now I want to modify the contract in such a way that only the owner can call the setter functions. As we've already seen in the last project, it's typical to use the require function to check for a condition. So at the beginning of the functions, I'm adding require owner equals msg.sender. I'm copying this line to clipboard and pasting it in the second function as well. This means that the body of the function will be executed only if the condition of the require function returns true, so if the account that calls the function is the owner or the one that has deployed the contract. This is okay, but we could do better. We've used the same condition in both functions, and this means redundant code. If we want to change the condition in any way, we have to change both functions, and that's prone to errors. This is a very simple example, but imagine a more complex project with many functions and lots of conditions. A better alternative would be to create a function modifier and use it when declaring our functions. So, modifier only owner. And in the function modifier, I'm writing require owner equals msg.sender. The same condition I've used in the setter functions. And an underline and a semicolon. Let's discuss this piece of code. You create a function modifier just like a normal function using the modifier keyword instead of function. The require function with the same condition is called inside the modifier, and on the next line there's a special statement. Underline, semicolon. Now I'm applying the modifier to our functions. So after the public keyword, I'm adding the name of the modifier. Only owner. And I'm removing require from the function's body. We have the same contract, just that there's no redundant code and it's more readable. In Solidity, this is the idiomatic way of testing specific conditions before executing a function. Let me tell you a few words about this statement. Underline, semicolon. What it does is that the function's body is inserted where the special symbol underline appears in the definition of the modifier. This means that if the owner calls this function, the function is executed and otherwise an exception is thrown. Let's test the contract. I'm using the JavaScript VM environment, and using the first account, I'm deploying the contract. The owner is the address that has deployed the contract, and the price is 0, the default value for an unsigned integer. I'm selecting another account, and I'm trying to change the owner and the price. For example, I want this address to be the new owner. I'm pasting it here and clicking change owner. And I've got an error. This account is not allowed to call this function, change owner. I'll get the same result for a set price as well. Now, I'm selecting the owner account, the first one. And I'm clicking change owner. And the transaction executed successfully. The owner was able to call the change owner function and change the owner. So the new owner is this account, the one that starts with 617. This is the new owner. Okay, we've just seen how to declare and use function modifiers. In this lecture, we'll see how a user can place a bid. We'll declare a payable function called placeBid that will be called when someone wants to place a bid. Function placeBid public, and payable. There are some restrictions in calling this function. First of all, we don't want to allow the owner to place a bid because he could increase the price artificially. So I'm declaring a function modifier called notOwner that will be applied to the placeBid function. Modifier notOwner. And inside the modifier, require msg.sender is not equal to the owner. So the address that calls the function is not the owner. And underline semicolon. Another restriction will be that the auction will be running only between the start and end blocks. So I'm creating another two modifiers. Modifier after start and require block.number greater than or equal to start block. Underline semicolon. And the second modifier before end. So modifier before end and the require function. Require block.number is less than or equal to end block. And I'm applying the modifiers to the function. So notOwner after start and before end. Inside the function, I'm adding other two restrictions. For someone to be able to place a bid, the auction should be in the running state and the minimum bidding value should be 100 Wei. I think in a real example, you could increase it to 0.01 Ether or something that best fits your need. But for our tasks, 100 Wei is just fine. So require auction state equals state dot running. So the auction is in the running state. And also require msg.value greater than or equal to 100 Wei. And now the logic of the function. Let's see what really happens when someone places a bid. Take a look at this slide. There are two bidders in the bids mapping variable. The keys of the mapping are the addresses of the bidders and the values in Wei sent in the auction. So the first bidder has sent 40 Wei, the second one has sent 70, and the bid increment is 10. At this moment, the highest bidder is the second one, and the highest binding bid is 50. The minimum between all the bids plus the bid increment, which is 10. So 40 plus 10 equals 50. The application automatically bids in increments of 10. Now let's suppose that the first bidder wants to outbid the highest bidder. So the address 123, the first one, is sending 15 Wei. What will happen? So the mapping variable will look like this. Bids of 0x123 equals 40, the previous value sent, plus 15, the current value, equals 55. And the highest binding bid will be the minimum between all the bids, so between 55 and 70, plus the bid increment, which is 10. So highest binding bid equals mean of 55 plus 10 and 70 equals 65. If the auction gets finalized right away, 65 will be the selling price. It won't be 70 because the application automatically bids in increments of 10 up to a maximum value, which is the highest bid. Let's return to the smart contract. I'm declaring a local variable of type uint called current bid. This will be the value already sent by the current address plus the value sent with this transaction. So uint current bid equals bids of msg.sender, the value the current user has already sent, plus msg.value, the value sent with this transaction. In this example, the current bid is 55. The sum between the value already sent, which is 40, plus the current value, which is 15. This is the current bid. And if this is the first time when this address places a bid, then the current bid is the value sent with this transaction because bids of msg.sender is 0. So this value is 0. 0 is the default value of any key in the mapping, so also of an address that does not already exist in the mapping. This seems a little bit strange because you expect to bid the entire amount each time, not the extra amount over the current value. Or if you have already bid $80 for a product on eBay and somebody else outbids you by bidding 90 and you want to outbid the other person, then you will bid 100, not 20. Our contract has a different logic, but from the user's point of view, it will be the same. In the contract's frontend, we'll allow the user to bid the entire amount, and behind the scenes, we'll do the math, so that the smart contract uses the logic I've shown you. We'll also have a new requirement. What if the user bids a lower value, let's say 5? The current bid is 45, which is less than the highest binding bid, which is 50, and the function should stop. There's nothing to be done in this case. I'll put back the initial values. So the requirement will be that the current bid should be greater than the highest binding bid. Require current bid greater than highest binding bid. Next, we are updating the bids variable for the current user. So bids of msg.sender equals current bid. Now, there are two possibilities. The current bid, which is 55, is greater than the highest binding bid, which is 50, but is less than bids of highest bidder, 70 in this example. So 55 is greater than 50, but 55 is less than 70. In this case, the highest bidder will remain the same. So if current bid less than or equal to bids of highest bidder. And I'm calculating the highest binding bid as being the minimum between the current bid plus the bid increment and the bids of highest bidder. I've already explained to you the logic behind all of this. So highest binding bid equals min of current bid plus bid increment and the bids of highest bidder. Take a look at this error. In Solidity, there's no function that returns the minimum between two values, so I have to create one. So function min uint a, uint b. The function is pure. It neither alters the blockchain nor it reads from the blockchain. Internal, and returns an uint value, the minimum between a and b. And if a less than or equal to b, return a. Else, return b. This is our function. This is a helper function. Okay, let's return to the placeBid function. In this case, the highest bidder remains unchanged. Else, this else branch gets executed when the current bid is greater than bids of highest bidder. Let me show you an example. Let's suppose the first address is sending 100 way. The current bid will be 40 plus 100 equals 140. What is the highest binding bid in this case? It's the minimum between the current bid, so 140, and the previous highest binding bid, which was 70, and the bids of highest bidder, which is 70, plus the bid increment, so plus 10. So the highest binding bid is 80. 10 over 70. So highest binding bid equals min of current bid and the bids of highest bidder plus the bid increment. And I'm also changing the highest bidder because the current bidder became the highest bidder. So highest bidder equals payable of msg.sender. The current address converted to a payable one. And that's all. This was the main function of the auction, and there are lots of details. Take your time to deeply understand how it works. We are taking a short break, and in the next lecture, we'll test the place bid function. Let's go ahead and see how the auction can be cancelled. If an emergency like a vulnerability is found in the code or anything bad happens, the owner has the possibility to cancel the auction so that all the bidders can request back their funds. First, I'm creating a new function modifier called onlyOwner that will be applied to any function that should be called by the owner only. Modifier onlyOwner. Require msg.sender equals owner. Underline and semicolon. Next, I'll create a function called cancel auction. Function cancel auction public and the function modifier only owner. The function can be called only by the owner, and inside the function I'm setting the auction state to cancelled. So auction state equals state.cancelled. What will happen when someone wants to place a bid after the auction has been cancelled by the owner? The first require of the place bid function checks if the auction is in the running state. If the condition is not true, the transaction will be stopped and the bid will not be placed. Let's test it. Using the first account, I'm deploying the contract. The contract was deployed and I'm trying to cancel the auction using another account. I'm selecting a random account and I'm clicking cancel auction. And I've got an error. Only the owner can cancel the auction. Now I'm selecting the owner account, so the first one, and I'm canceling the auction. And the transaction executed successfully. The owner could cancel the auction. Let's see what is the auction state. And it returned 3. Take a look here. 3 means cancelled. Started is 0, running is 1, ended 2, and cancelled 3. If any other user tries to place a bid, he will get an error. I'm placing a bid using a random account. And I've got an error. The first require of the place bid function stopped the transaction. An auction like ours needs a simple front-end interface that allows the users to withdraw their funds after the auction is complete and they didn't win, or if the auction has been cancelled. We don't proactively send back the funds to the users that didn't win the auction. We'll use the withdrawal pattern instead. After the DAO hack, which was one of the most famous attacks on an Ethereum smart contract, a new best practice has been identified and generally accepted. A smart contract only sends ETH to the users when they explicitly request it. This is known as the withdrawal pattern and helps us avoid reentrance attacks that could cause unexpected behavior of a smart contract, including catastrophic financial loss for the users. Let's dive deeper into it and give an example. A user places a bid from another smart contract with a malicious crafted receive or fallback function designed to consume all of the gas provided to it. This user could never be outbid because when someone else tries to place a higher bid, the EVM would send the Ether back to the smart contract with the malicious function. The user was outbid and the funds must be sent back. But the transaction would run out of gas, preventing the new users from placing a higher bid. As a conclusion, after the auction ends or gets cancelled by the owner, we don't automatically send the funds back to the bidders. The bidders must call themselves the function that will transfer the funds back to their account. We'll go ahead and create the function that finalizes the auction when it ends or gets cancelled. So function finalize auction and public. We are starting by calling the require function to check if the auction ended or was cancelled. So require auction state equals state.cancelled. This means it was cancelled. Or block.number greater than end block. This means that the auction ended. I've used the logical OR operator, which means that the require function returns true if any of the two conditions is true. If the auction was cancelled by the owner or ended, it can be finalized by either the owner or by any bidder. So, require msg.sender equals owner. The logical OR operator bids of msg.sender greater than 0. What does this mean? It means that msg.sender, the account that wants to finalize the auction by calling this function, is a bidder. Only a bidder is registered in the bids mapping with a value greater than 0 for his address. This practically means that either the owner or a bidder can finalize the auction. Next, I'll find the address that will receive the funds sent in the auction. I'm declaring a local variable of type address called recipient and another one of type uint called value. So address, payable, recipient. And the uint value. There are two possibilities. The auction was cancelled and everybody can request and get all the money they've sent, or the auction ended and the owner receives the highest binding bid. So if auction.state equals state.cancelled, so this means auction was cancelled. It was cancelled and every bidder requests and gets his own money. So recipient equals payable of msg.sender. The recipient is the bidder that will call the function to get its money back. And value equals bids of msg.sender. This is the value the bidder has already sent in the auction. Else, this else branch will execute if the auction ended. So I'm writing here a comment to make it clear. Auction ended, not cancelled. If the auction is finalized by the owner, he will receive the highest binding bid. So if msg.sender equals owner, this is the case when the owner comes to get his money. This is the owner. The recipient is the owner, and the value is the highest binding bid. And there's another else branch. The address that finalizes the auction is not the owner, but a bidder who requests his own funds. So this is a bidder. And there are two possibilities as well. If the one that calls the function is the highest bidder, he receives the difference between the value he bid and the highest binding bid. Take a look here to make it clear, the highest bidder is the first address and has bid 140. The selling price is 80, so he will get back the difference. 140 minus 80 equals 60. If this is the highest bidder, msg.sender equals highest bidder. The highest bidder is the recipient, and the value is equal to bids of highest bidder, the value he sent in the auction, minus the selling price, the highest binding bid. And another else, I promise you, this is the last one. This is the case when this is neither the owner nor the highest bidder. It's one of the bidders of the auction. Recipient equals payable of msg.sender, the address of the bidder, the one that calls the function, and value equals bids of msg.sender. The value the bidder bid. Now I'll transfer the value to the recipient. Pay attention to all these if-else branches. This is the contract level curly brace. This is the function curly brace. So I'll write the code here. Before the ending function curly brace. So recipient dot transfer of value. And that's all. This is the finalize auction function. In the next lecture, we'll test the entire contract. See you in a second. I've just developed a smart contract for a decentralized auction. Now it's time to test it and see how it works. Just for our tests, I'll make a few small changes. I'll deploy the contract in the JavaScript virtual machine, and each transaction will be in its own block and it starts from 0. So I want the auction to end after 3 transactions, not after more than 40,000. And I'll change the increment to be 1 ETH, not 100 WEI, because I want to bid in ETH. Let's see the value of 1 ETH in WEI. I'm pasting it here. This means 1 ETH in WEI. Now using the first account, I'm deploying the contract. That account is the owner. If I try to bid using the owner, the first account, I'll get an error because the owner is not allowed to place a bid. Take a look at this modifier, not owner. I'm trying to send 1 ETH in the auction using the first account. And there was an error. I'm placing the first bid of 2 ETH using the second account and calling the place bid function. 2 Ether and place bid. The third account will bid 4. And the next one, 7 Ether. If you get an error when placing the third bid, just refresh the browser and start it all over again. Or replace here 3 by 4. This is because I've used a transaction, so a block, when I tested if the owner can bid. There are 3 bidders, and let's see the state variables. The auction is still running. The highest bidder is the last account. he bid 7. The highest binding bid is only 5, not 7, because the application has automatically bid the increment, which is 1 ETH, over the second bidder, who was the highest bidder before the third address placed the bid. If you want to see the value a user sent, just copy his address and paste it in the bids field here. So this account has bid 2 Ether. I'm selecting the owner account and canceling the auction. Let's see the auction state. The auction state is now 3, which means cancelled. Remember that an enum variable is implicitly convertible to int and it starts from 0. Let's take a look at the finalize auction function. The auction was cancelled, so what will happen? This piece of code will get executed. So in this case, every bidder can request and receive his own money. Let's try this. I'm selecting the second account and I'm calling the finalize auction function. And we notice that it has received back 2 Ether. Now its balance is almost 100 Ether. It paid for the gas, so that's why its balance is less than 100. And I'll do the same for the other 2 accounts. And the last one. Everybody received his own money back. Let's see the value that was bid by an address. So I'm copying the address and pasting it here. The finalize auction function works as expected when the auction is cancelled by the owner. Now let's test what will happen if the auction ends after a specific amount of time. I'm reloading the web page to restart the JavaScript virtual machine environment. I'm deploying the contract using the first account and I'm placing 3 bids in the auction using the following 3 accounts. Okay, I'm done. I've said that the auction ends in 3 blocks, and in JavaScript virtual machine, each transaction is in its own block. So the auction will be ended when I call the finalize auction function. Before finalizing it, let's see which are the highest bidder and the highest binding bid. The highest bidder is the last address, the last user. He bid 7 Ether. And the highest binding bid is 5 Ether. 1 over the previous highest bidder, which was the second account that bid 4. And I'm finalizing the auction using the owner account. The auction was finalized. We see how the owner received the highest binding bid, which was 5, and the highest bidder, the difference between the amount he bid and the highest binding bid, or the price he paid for the product or service. And the last bidder can do the same. Okay, every bidder got the money back. The front-end offered by Remix is simple but efficient, and we can also create a fancy website that uses the Web3.js library to interact with the Ethereum network. And that's all. The smart contract works just fine. But if you are not experienced with Solidity and smart contract programming, you won't notice that there's a big security vulnerability. We are taking a short break, and in the next lecture, we'll deal with the vulnerability I've just mentioned above. I've just developed a smart contract for a decentralized auction. Now it's time to test it and see how it works. Just for our tests, I'll make a few small changes. I'll deploy the contract in the JavaScript virtual machine, and each transaction will be in its own block and it starts from 0. So I want the auction to end after 3 transactions, not after more than 40,000. And I'll change the increment to be 1 ETH, not 100 WEI, because I want to bid in ETH. Let's see the value of 1 ETH in WEI. I'm pasting it here. This means 1 ETH in WEI. Now using the first account, I'm deploying the contract. That account is the owner. If I try to bid using the owner, the first account, I'll get an error because the owner is not allowed to place a bid. Take a look at this modifier, not owner. I'm trying to send 1 ETH in the auction using the first account. And there was an error. I'm placing the first bid of 2 ETH using the second account and calling the place bid function. 2 Ether and place bid. The third account will bid 4. And the next one, 7 Ether. If you get an error when placing the third bid, just refresh the browser and start it all over again. Or replace here 3 by 4. This is because I've used a transaction, so a block, when I tested if the owner can bid. There are 3 bidders, and let's see the state variables. The auction is still running. The highest bidder is the last account. He bid 7. The highest binding bid is only 5, not 7, because the application has automatically bid the increment, which is 1 ETH, over the second bidder, who was the highest bidder before the third address placed the bid. If you want to see the value a user sent, just copy his address and paste it in the bids field here. So this account has bid 2 Ether. I'm selecting the owner account and cancelling the auction. Let's see the auction state. The auction state is now 3, which means cancelled. Remember that an enum variable is implicitly convertible to int and it starts from 0. Let's take a look at the finalize auction function. The auction was cancelled, so what will happen? This piece of code will get executed. So in this case, every bidder can request and receive his own money. Let's try this. I'm selecting the second account and I'm calling the finalize auction function. And we notice that it has received back 2 Ether. Now its balance is almost 100 Ether. It paid for the gas, so that's why its balance is less than 100. And I'll do the same for the other 2 accounts. And the last one. Everybody received his own money back. Let's see the value that was bid by an address. So I'm copying the address and pasting it here. The finalize auction function works as expected when the auction is cancelled by the owner. Now let's test what will happen if the auction ends after a specific amount of time. I'm reloading the web page to restart the JavaScript virtual machine environment. I'm deploying the contract using the first account, and I'm placing 3 bids in the auction using the following 3 accounts. Okay, I'm done. I've said that the auction ends in 3 blocks, and in JavaScript virtual machine, each transaction is in its own block. So the auction will be ended when I call the finalize auction function. Before finalizing it, let's see which are the highest bidder and the highest binding bid. The highest bidder is the last address, the last user. He bid 7 Ether, and the highest binding bid is 5 Ether. 1 over the previous highest bidder, which was the second account that bid 4. And I'm finalizing the auction using the owner account. The auction was finalized. We see how the owner received the highest binding bid, which was 5, and the highest bidder, the difference between the amount he bid and the highest binding bid, or the price he paid for the product or service. And the last bidder can do the same. Okay, every bidder got the money back. The frontend offered by Remix is simple but efficient, and we can also create a fancy website that uses the Web3.js library to interact with the Ethereum network. And that's all. The smart contract works just fine. However, this is just for one auction, and we want a contract that implements tens or hundreds of auctions. We are taking a short break, and in the next lectures, we'll talk about scalability and how to deploy and control hundreds of auctions. We've developed a smart contract for a decentralized auction, like an eBay replacement. However, the contract is for only one auction. Now, it's time to talk about scalability. If we take a look at a web application like eBay, we'll see that there are thousands of auctions and each of them has its own admin or owner. For example, if I'm searching for hardware wallet on ebay.com and then selecting auction, I've got lots of products, each being an independent auction. By the way, I recommend you to buy and use a hardware wallet if you want to store your cryptocurrencies securely. So the most important question is, how can we scale our application from one auction to hundreds of auctions? Let's dive deeper into this. First of all, each auction will have its own owner. Different users will come and create their own auction, so somehow we must permit them to do that. We cannot do that for them. Here, there are more possibilities. One approach would be that when a new user clicks a button such as Create New Auction, we send him the contract's bytecode, so the compiled version of the contract. Then the user using MetaMask or another decentralized browser will deploy the contract, so his new auction. He has to return to us the new contract's address to display details about the new auction on the website. If we take this approach, there will be a problem, a security one. If we send the contract's bytecode to a third party, which we don't trust, that party can alter the bytecode and remove some restrictions. For example, he could remove the not owner modifier or any other restriction, and this is not good. We could have a very serious security hole in our application. So what should we do? The best approach is to create another contract, which is a creator contract that calls a function that deploys a new instance of the actual auction contract. That means that when a user wants to deploy a new auction contract for a product or service, he simply calls a function of the creator contract, which we control. We are the owner of the creator contract, and by calling a function of the creator contract, a new instance of the auction will be deployed, and the user is the one that will pay for the gas because he calls the function that deploys the contract. This way, he doesn't have access to the contract's bytecode, and there's no possibility for a malicious user to alter and to exploit the contract. As a conclusion, we'll scale and secure the deployment of thousands of auctions by creating a new contract that will deploy the auction contract. The users will simply click a button like Create Auction, and a function of the creator contract will deploy a new auction for them. Each user will be the owner of his own auction and will pay for the transaction that creates the auction. We'll also save the addresses of all auctions to have access to them and display them on the front end of the web application. We are taking a short break, and in the next lecture, I'll show you how a contract deploys another contract and how to solve different issues that may appear. We are starting from an empty contract. I'm just declaring a state variable of type address called owner that will be the address that deploys it. Address public owner A. I'm declaring the constructor and initializing owner A to msg.sender, the address that deploys the contract. Owner A equals msg.sender. We can deploy the contract as usual, and the address that deploys the contract will be the owner. So the first address is the owner. This contract can be deployed by an externally owned account or by another contract. We've seen the first option, so let's take a look at how a contract deploys another contract. I'm creating a new contract that will deploy contract A. Let's say contract creator. And I'm declaring a state variable of type address that is the owner of the contract called creator. Address public, owner, creator. I'm declaring the constructor and initializing owner creator to msg.sender, the address that deploys it. Now, I'm declaring a function that will deploy contract A. It will create a new instance of A when will be called function deploy A public. And I'm writing A, the name of the contract, let's say new A address equals new A and a pair of parentheses. I've created a variable of type contract A, and that means that I've created an instance of A. This is how a contract deploys another contract. Keep this in mind. The address of the new instance of A should be saved because we'll need it. So I'm declaring a dynamic array that will store elements of type addresses of instances of A. So A, a pair of square brackets, this means a dynamic array with elements of type instances of A, public, and the name of the variable deployed A. And I'm adding or pushing the new address to the dynamic array. So deployed A dot push new A address. Let's test the contract. I'm using the first account and I'm deploying the contract called creator. I'm selecting creator and clicking deploy. This is the contract's interface, and I'm creating a few instances of contract A. So I'm clicking deploy A. I've created an instance of A, another instance of A, and another one. So I've created 3 instances of A. The addresses of the new instances are saved in the dynamic array, so in deployed A. If I want to see the first address, I have to get the elements at index 0. This is the first address of contract A. This is the address of the second instance and the address of the last one. I'm selecting this address and loading the contract. Copy. I'm pasting here at address and I'm selecting A and clicking at address. And contract A was loaded. Let's check the owner of contract A. This address is the owner. We can see that this address is the address of the contract called creator. It starts with 7EF, the same as the address of the creator. It's not the address of the account that called deploy A, so of this account. Sometimes we want that even though a contract is deployed by another contract, the owner of the deployed contract should be the externally owned account that called the function that deployed the contract. Deploy A in this case. This is also the case of our auction contract. The auctions will be deployed by another contract, but we want the owner of the auctions to be the user that sells the good or service, not the creator contract. Each auction will have its own owner. So I'll pass the address that calls deploy A, this function, to the constructor of A and initialize owner A, this variable, to that address. So here I have new A of msg.sender. I'm passing msg.sender, the externally owned account that calls the function, to the constructor of A. And in the constructor of contract A, I'm adding address EOA, externally owned account. And owner A will be EOA. So msg.sender will be passed to the constructor as EOA, and owner A will be initialized with that address. Let's test it. Using the first account, I'm deploying the contract, the creator contract. I'm selecting creator and deploy. Now I'm selecting another account, a random one, and I'm creating an instance of A. Let's see the address of the instance. I'm copying the address, pasting it here at address, selecting A and clicking at address. And contract A was loaded. Let's see who's the owner of contract A. And we see that the owner is an address that starts with 1, A, EO, EA, and so on. It's this account, the externally owned account that has called deploy A. We are taking a short break, and in the next lecture we'll change the auction contract so that it gets deployed by another contract. In this lecture, we'll create a new contract called auction creator with a function called createAuction that will create a new instance of an auction. This is the auction contract we've deployed in the previous lectures. And I'm creating the new contract. Contract auction creator. I'm declaring a dynamic array that will store the addresses of the deployed auctions. Auction, a pair of square brackets, public auctions. Now I'm declaring the createAuction function, and when called, it will create an auction. Function createAuction. This is a public function. Inside the function, I'm creating a variable of type auction, which means in fact deploying an auction. Auction, new auction, the name of the variable, equals new auction and a pair of parentheses. Here I'm calling the constructor. So I'm creating a new auction. And I'm adding the address of the contract to the dynamic array because we'll need it later. So auctions.push and new auction. When the user calls the createAuction function of this contract, the function will create an auction, and the owner of the auction will be the address of the contract, not the address of the externally owned account that calls it. As we've already seen in the last lecture, this is not good. We need the owner of the auction to be the address of the externally owned account that creates the auction by calling this function. We've already gone into this in the previous lecture, so I'm making some changes. I'm passing msg.sender, the address that calls the createAuction function, to the constructor of the auction contract. And I'll modify the constructor. I'm adding a new parameter, address, EOA, externally owned account, and the owner will be equal to Payable of EOA. And that's all. I'm testing the contract. I'm selecting the first account and I'm deploying the auction creator contract. Now I'm selecting a random account and I'm clicking on create auction. So in fact, I have deployed an auction. Let's see the address of the new auction. This is at index 0. This is X address. I'm copying it to clipboard, pasting it in at address, selecting auction and clicking at address. I've loaded the auction in Remix. This is my auction. Let's see who's the owner. And we see that the owner is the externally owned account that clicked create auction and created the auction. Is this account. Okay, and that's all. This is the final version of our auction smart contract. Note that we've tested it using Remix because creating frontends at this moment is not our main purpose. You can dive into that after you become proficient in Solidity. Of course, we can create a fancy website using a JavaScript framework and the Web3.js library that connects to the Ethereum blockchain the same way Remix does. Hello guys and welcome back. In this lecture, we'll start developing our own ERC20 token. This is the interface any fully compliant ERC20 token should implement. There are 6 functions and 2 events that should be overridden in the token contract. Note that for a functional token that can be transferred from one address to another, not all 6 functions are mandatory, but only the first 3. So, I'll start creating the token contract and override those functions. I'm declaring a new contract called Cryptos that derives from the ERC20 interface. Contract Cryptos is ERC20 interface. This is the token contract. There's an error because the contract doesn't implement all the functions of the interface from which it derives. We'll ignore it for the moment. I am declaring the state variables of the contract. Please use the exact names that I'll use, since most of them are part of the standard. The first state variable will be called name and will hold the name of the token. So string public name equals Cryptos. Each token or cryptocurrency has its own symbol, such as BTC for Bitcoin or ETH for Ether. It's like a stock ticker, and even though it has no restriction on its size, it is usually 3 or 4 characters long. So the next state variable will be called symbol. String public symbol equals CRPT. The next one will be the decimals, and it refers to how divisible a token can be. In general, its range is from 0 to 18. Technically speaking, the decimal's value is the number of digits that comes after the decimal place. So uint public decimals equals 0. 18 is the most used value for the decimals state variable, but to keep it simple, I'll use 0 in this example. The next variable will be called total supply and represents the total number of tokens. Note that there's already a function called total supply in the interface, so I must override it using the override keyword. So uint public override total supply. The override keyword is necessary because in fact it creates a getter function called total supply because the variable is public. And one of the rules we've seen when we talked about interfaces says that functions must be overridden using the override keyword. I'd have one remark here. As you can see, to improve usability, the ERC20 standard defines some functions, though many of them being optional. These functions are name, symbol, decimals, total supply, so they have the exact name as our state variables. Name, symbol, decimals, total supply. What will happen here is that functions with the same names as the public variables will be created. So, in fact, declaring these state variables as being public, we've also created the functions, these functions. This is why it's important to use the exact names you see here. Next, I'm gonna add a few other state variables. The first one is founder and is the address that deploys the contract and has all the tokens in the first place. This is not part of the ERC20 standard, but it's useful. So address public founder. The next state variable will be called balances of type mapping. The keys will be of type address and values of type uint. In this variable will be stored the number of tokens of each address. Note that each Ethereum address can have a number of tokens, and by default the value of any address will be 0 because this is the default value of an uint variable. So mapping address uint and public balances, the name of the variable. For example, if an address receives 100 cryptos from the founder, then we'll have balances of and the address equals 100. This is how the contract will store the tokens of each address. Okay, that's all. We are taking a short break, and in the next lecture, we'll define the mandatory functions of an ERC20 token.